everyone, and welcome back to Scientific Discovery Hub. Have you ever wondered if something from another star system could knock on our cosmic door, carrying secrets of the universe? Well, meet 3I Atlas, a mysterious interstellar comet that zipped through our solar system in 2025, sparking wild questions about black holes, rogue planets, and the very fabric of space itself. In this video, we'll unravel the mind-blowing story of this cosmic traveler and explore whether it brushed past hidden giants in the dark. Discovered by the Atlas survey, 3I Atlas isn't your average comet. It hurtles through space at 58 kilometers per second, fast enough to escape the sun's gravity entirely. Its hyperbolic path screams interstellar origin, making it only the third known object to visit us from beyond the solar system. But where did it come from? Could its journey have been shaped by a rogue planet, a homeless world drifting through the galaxy, or even a black hole whose gravity could slingshot it across the cosmos? We'll break down the science in simple terms, from decoding its galactic origins, hint it might be older than Earth, to peering into its red-hued coma of gas and dust, which hides clues about alien chemistry. Was 3I Atlas nudged by unseen forces like rogue planets or warped spacetime near a black hole? And what does its journey tell us about the Fermi paradox, the nagging question of why we haven't found more evidence of life in the universe? Whether you're a space enthusiast or new to astronomy, this video will take you on a thrilling ride through orbital mechanics, cometary chemistry, and the profound connections tying our galaxy together. Along the way, we'll ask, are we truly alone, or are we just one thread in a vast interstellar tapestry? Hit play to dive into the full breakdown, and don't forget to subscribe for more deep dives into the wonders of science. Let's explore the universe one cosmic mystery at a time. In the vast expanse of the cosmos, where stars burn in silent brilliance and galaxies spiral in endless dance, a visitor has arrived. 3I Atlas, the third interstellar object ever recorded within our solar system, drifts through the void, carrying with it the echoes of distant stellar nurseries and the secrets of a galaxy teeming with unseen travelers. Discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, Atlas Observatory in Chile, this enigmatic comet does not belong to our celestial backyard. It hails from beyond the gravitational embrace of the Sun, a relic of another star's birthplace, now passing through our cosmic neighborhood on a trajectory that will forever take it back into the abyss of interstellar space. Unlike the familiar comets that originate from the Kuiper Belt or the distant Oort cloud, 3I Atlas moves at an extraordinary speed, 58 kilometers per second, far exceeding the velocities of native solar system bodies. This rapid motion, combined with its hyperbolic trajectory, confirms that it is not bound by the sun's gravity and has traveled here from the depths of interstellar space. Its passage through the inner solar system is fleeting, a brief moment in cosmic time, yet it offers an unprecedented opportunity to study the composition and dynamics of an object born in another planetary system. As 3I Atlas glides past the orbits of Earth, Mars, and Jupiter, it carries with it the chemical signatures of its alien origin, revealing the building blocks of worlds far removed from our own. What makes 3I Atlas particularly fascinating is its apparent activity. Though shrouded in a coma of gas and dust, the comet is actively outgassing, releasing carbon dioxide, water ice, and other volatile materials into space. These emissions suggest that it is not merely a lifeless rock, but a dynamic world responding to the sun's warming touch. The James Webb Space Telescope has already detected the presence of carbon dioxide in its coma at unexpectedly high levels, a finding that challenges our understanding of cometary chemistry. Could this be the result of a different formation process, one shaped by conditions in a distant star system? Or does it hint at a unique evolutionary history, one that defies the patterns we observe in our own solar system? As 3I Atlas continues its journey, it reminds us that we are not alone in the universe. The realization that interstellar objects exist in numbers far greater than previously imagined has reshaped our perception of the cosmos. Once considered rare anomalies, These visitors now appear to be a natural consequence of the gravitational chaos that governs the universe. Every star system, it seems, casts off fragments of its youth, sending them adrift on lonely voyages through the galactic dark. In the case of 3I Atlas, we have been granted the privilege of witnessing such a voyage firsthand, a fleeting encounter between two cosmic realms, separated by the vastness of space yet connected by the fundamental forces that shape the universe. The discovery of 3I Atlas marked a pivotal moment in observational astronomy, revealing the intricate dance of celestial mechanics that governs the movements of interstellar objects. On 1 July 2025, the Atlas Observatory in Rio Hurtado, Chile, captured the first glimpse of this enigmatic visitor as it traversed the inner solar system at a velocity of 58 kilometers per second. At that time, 3I Atlas was situated at a distance of 4.5 astronomical units (AU) from the Sun, placing it beyond the orbit of Jupiter. Its trajectory, however, was unmistakably different from that of any native solar system object. The comet's hyperbolic path, characterized by an orbital eccentricity of 6.141 NAS.002, immediately signaled its interstellar origin. Unlike the elliptical orbits of planets and comets bound to the Sun, this trajectory suggested that 3I Atlas was not a product of our celestial neighborhood, but a traveler from another star system. The hyperbolic nature of 3I Atlas's orbit is a direct consequence of its immense speed. Objects within the solar system are held in place by the Sun's gravitational pull. Their trajectory is determined by the delicate balance between inertia and gravitational attraction. 3I Atlas, however, moves at a velocity that exceeds the escape velocity of the solar system, meaning that no matter how close it comes to the Sun, it will never be captured into a permanent orbit. Instead, it will continue its journey outward, eventually vanishing into the depths of interstellar space. This distinction is crucial, as it places 3I Atlas in a rare category of objects, interstellar interlopers that traverse the cosmos unbound by the gravitational anchors of any star. The precise determination of 3I Atlas's trajectory required extensive follow-up observations from telescopes around the world. In the days following its discovery, astronomers scrambled to refine its orbit using data from the Zwicky Transient Facility, the Lowell Discovery Telescope, and the Canada-France-Hawaii Telescope. These efforts revealed that 3I Atlas had already passed through the inner solar system in late June 2025, but its presence had gone unnoticed due to its position near the dense star fields of the galactic center. The comet's proximity to this region made it difficult to distinguish against the backdrop of millions of stars, a challenge compounded by its relatively faint luminosity. By 2 July 2025, the International Astronomical Union's Minor Planet Center had officially classified 3I Atlas as an interstellar object, assigning it the designation 3I. This classification followed the precedent set by 1I Oumuamua in 2017 and 2I Borisov in 2019, marking the third confirmed interstellar visitor to our solar system. What set 3I Atlas apart from its predecessors was not only its trajectory, but also its clear cometary activity. Unlike 1I Oumuamua, which exhibited no signs of outgassing, and 2I Borisov, which displayed a more typical cometary behavior, 3I Atlas revealed itself as a dynamic world, actively shedding material as it approached the Sun. The initial observations of 3I Atlas were met with a mix of skepticism and excitement. Some astronomers questioned whether it was truly a comet, or perhaps an asteroid that had been misidentified due to observational limitations. However, subsequent analyses confirmed the presence of a coma, a diffuse cloud of gas and dust surrounding the nucleus, indicating that the object was indeed a comet. The coma, composed primarily of carbon dioxide and water ice, expanded as 3I Atlas neared the Sun, its volatile ices sublimating under solar heating. This process, known as outgassing, is a defining characteristic of comets and provided strong evidence that 3I Atlas was not an inert rock, but a dynamic celestial body responding to the Sun's influence. As the comet continued its inward journey, astronomers tracked its evolution with increasing precision. The Hubble Space Telescope, the James Webb Space Telescope, and ground-based observatories, such as the Very Large Telescope, contributed to a growing body of data that painted a clearer picture of 3I Atlas's nature. These observations revealed that the comet's nucleus was likely less than a kilometer in diameter, significantly smaller than the sizes estimated for its earlier counterparts. Despite its modest size, 3I Atlas was producing a coma that spanned thousands of kilometers in diameter, a testament to the intensity of its outgassing activity. The red hue of 3I Atlas's coma, detected through spectroscopic analysis, added another layer of intrigue. This coloration, similar to that of 2I Borisov, suggested the presence of irradiated organic compounds, possibly the remnants of ancient molecular clouds, or the byproducts of prolonged exposure to cosmic radiation. Such findings hinted at the comet's long and eventful journey through interstellar space, during which it may have encountered various stellar environments and interstellar phenomena. With each passing day, the trajectory of 3I Atlas brought it closer to the inner solar system, setting the stage for a series of close approaches to planets such as Mars and Venus. These encounters, though not posing a threat to Earth, offered valuable opportunities for further study. The comet's closest approach to the Sun, scheduled for 29 October 2025, would mark the peak of its activity, as solar heating intensified the sublimation of its ices and the release of dust and gas. The path of 3I Atlas, meticulously charted by astronomers, stands as a testament to the power of modern observational techniques. From its initial detection to the refinement of its orbit and the analysis of its composition, every step in its study has deepened our understanding of interstellar objects and their significance in the cosmic tapestry. As the comet hurtles toward perihelion, the questions surrounding its origin and nature continue to unfold, inviting further exploration into the mysteries of the universe. As 3I Atlas continues its journey through the inner solar system, its composition and behavior offer tantalizing clues about its origins and the environments in which it formed. Unlike the icy bodies native to our own solar system, which predominantly consist of water ice mixed with frozen methane, ammonia, and other volatiles, 3I Atlas exhibits a distinct chemical profile. Observations by the James Webb Space Telescope, JWST, have revealed an unusually high abundance of carbon dioxide, CO₂, in its coma, surpassing the levels typically observed in solar system comets. This finding raises intriguing questions about the conditions under which 3I Atlas formed and whether its parent star system experienced a different evolutionary history. The presence of CO₂ in such quantities suggests that the comet may have originated in a region where temperatures were low enough for this compound to condense into solid form, possibly beyond the CO₂ frost line in its home system. The CO₂ frost line, analogous to the more familiar snow line where water ice can condense, marks a boundary in a protoplanetary disk where carbon dioxide transitions from gaseous to solid phase. This implies that 3I Atlas may have formed in a colder, more distant region of its parent star system, far beyond the reach of liquid water before being ejected into interstellar space. In addition to CO₂, the coma of 3I Atlas contains water ice, water vapor, carbon monoxide, CO and carbonyl sulfide OCS. The detection of water ice and vapor is significant, as these molecules are typically associated with comets in our own solar system. However, the ratio of CO₂ to water in 3I Atlas is notably higher than what is usually observed in native comets, further distinguishing it from its solar system counterparts. The presence of CO and OCS suggests that the comet's outgassing is driven by a complex mixture of volatile compounds, some of which may have been preserved in its nucleus for billions of years. These findings contribute to our understanding of the diversity of cometary compositions and hint at the possibility that interstellar comets may carry signatures of their formation environments in ways that differ from those of their indigenous counterparts. The outgassing activity of 3I Atlas is not limited to these major volatile species. Observations by the Very Large Telescope, VLT, have identified the presence of cyanide, CN, and atomic nickel vapor in the comet's coma. The detection of CN is particularly noteworthy, as this molecule is commonly associated with cometary activity and serves as an indicator of the presence of organic compounds. The fact that 3I Atlas is emitting CN in concentrations comparable to those observed in solar system comets suggests that the comet shares certain similarities with native comets in terms of its volatile chemistry. The presence of atomic nickel vapor, on the other hand, is more unusual. While nickel has been detected in cometary Comet before, such as in the case of 2I Borisov, the absence of detectable iron vapor in 3I Atlas is unexpected. Typically, nickel and iron are found in roughly equal proportions in cometary emissions, leading to speculation about the processes responsible for the selective release of nickel in this particular object. One hypothesis is that nickel may be released through the decomposition of nickel-containing organic compounds, such as nickel tetracarbonyl, under the influence of solar radiation or space weathering. However, the precise mechanisms remain a subject of ongoing investigation. The composition of 3I Atlas is further illuminated by the red coloration of its coma, a feature shared with 2I Borisov and certain types of solar system comets. This reddish hue is attributed to the presence of irradiated organic compounds, which absorb blue light and reflect longer wavelengths, giving the coma its distinctive appearance. The organic material in the coma may have been altered over the course of the comet's interstellar journey, undergoing chemical transformations due to prolonged exposure to cosmic radiation. The presence of these compounds suggests that 3I Atlas may have retained a rich inventory of prebiotic materials, offering a glimpse into the chemical complexity that may be present in other planetary systems. Such findings have profound implications for our understanding of the distribution of organic molecules in the universe and the potential for life-supporting chemistry to exist beyond the confines of our solar system. As 3I Atlas approaches perihelion, the Sun's increasing influence will drive further outgassing and the expansion of its coma. The comet's activity is expected to intensify as solar heating accelerates the sublimation of volatile ices, leading to the formation of a more pronounced dust tail. Observations by the Hubble Space Telescope and the James Webb Space Telescope will continue to track these changes, providing insights into the dynamic processes shaping the comet's evolution. The anticipated increase in activity also raises the possibility of outbursts, sudden dramatic releases of gas and dust that could alter the comet's appearance and behavior. While no such outbursts have been observed thus far, the potential for such events underscores the unpredictable nature of cometary activity and highlights the importance of sustained monitoring. The study of 3I Atlas's composition and outgassing activity is not merely an academic pursuit. It holds the key to unraveling the history of interstellar objects and their role in the broader context of galactic evolution. By analyzing the chemical makeup of 3I Atlas, scientists hope to determine whether interstellar comets exhibit compositional trends that differ from those of their solar system counterparts, shedding light on the diversity of planetary systems across the galaxy. Furthermore, the detection of specific volatile species provides valuable constraints on the conditions under which 3I Atlas formed and the environments it may have encountered during its interstellar journey. These insights contribute to our growing understanding of the processes that shape the formation and evolution of comets, as well as the mechanisms by which they are ejected from their parent star systems. Ultimately, the composition and activity of 3I Atlas serve as a cosmic fingerprint, a record of its origins, and the history of its travels through the vastness of space. As astronomers continue to analyze the data gathered from this remarkable interstellar visitor, they are piecing together a more comprehensive picture of the universe, one in which comets like 3I Atlas play a vital role as messengers from distant stars. The origins of 3I Atlas are deeply entwined with the structure and history of the Milky Way, offering a rare glimpse into the ancient processes that shape interstellar objects. Tracing the comet's trajectory reveals that it entered the solar system from the direction of the galactic center, a region teeming with stars and interstellar material. More precisely, 3I Atlas is believed to have originated from either the thin or thick disk populations of the Milky Way. The thin disk, which includes the majority of stars in the galactic plane, is relatively young, with an average age of about 5 billion years. In contrast, the thick disk consists of older stars, many of which formed in the early universe, and have since migrated to their current positions. Given the high vertical velocity component of 3I Atlas, watts per 18.5 kilometers per second, astronomers have concluded that the comet likely belongs to the thick disk population, This distinction is significant because it implies that 3I Atlas may be significantly older than the solar system itself, which is approximately 4.6 billion years old. Studies conducted in July 2025 by Matthew Hopkins and collaborators estimated that 3I Atlas could be between 7.6 and 14 billion years old, making it one of the oldest interstellar objects ever observed. This estimation is based on the typical ages of stars in the thick disk, which tend to be older and have lower metallicities, measured by the abundance of elements heavier than helium compared to the Sun. The low metallicity of thick disk stars suggests that 3I Atlas may have formed in an environment where heavier elements were less abundant, a condition that could have influenced the composition of the comet and the nature of its parent star system. If 3I Atlas indeed hails from the thick disk, it may have originated in a protoplanetary disk that lacked the chemical richness of more recent star-forming regions, resulting in a unique set of volatile and refractory materials. The age of 3I Atlas is further supported by the compositional data gathered from its coma and nucleus. The high abundance of carbon dioxide, CO₂, in its coma as observed by the James Webb Space Telescope suggests that the comet may have formed in a cold, distant region of its parent star system, possibly beyond the CO₂ frost line. The presence of water ice, water vapor, carbon monoxide, CO, and carbonyl sulfide, OCS, further reinforces the notion that 3I Atlas originated in a chemically distinct environment. These findings align with the hypothesis that the comet is a remnant of an ancient planetary system, one that predates the formation of the solar system by billions of years. The fact that 3I Atlas has survived the vast expanse of interstellar space for such an extended period is a testament to the resilience of cometary bodies and the protective role of their icy nuclei in preserving primordial materials. The question of 3I Atlas's parent star remains unanswered, as the comet has been traveling through the Milky Way for so long that its origin cannot be definitively traced to a specific stellar system. However, indirect evidence suggests that it may have formed around a low metallicity star, one that has a significantly lower abundance of heavy elements compared to the Sun. This inference is based on the chemical composition of 3I Atlas, which lacks certain elements and compounds commonly found in comets from the solar system. The absence of detectable iron vapor in its coma, for instance, contrasts with the typical nickel-iron ratios observed in other comets, hinting at a different formation history. Additionally, the detection of irradiated organic compounds in its coma suggests that 3I Atlas may have spent a considerable portion of its existence in the cold, dark voids of interstellar space, where exposure to cosmic radiation has altered its chemical makeup. The journey of 3I Atlas through the Milky Way has not been a solitary one. AMPER's September 2025 study by Yang Guo and collaborators revealed that the comet may have passed within 1 parsec, 3.3 light-years, of 25 known stars in the past 10 million years. These close encounters, while not sufficient to alter its overall trajectory, could have subjected 3I Atlas to subtle gravitational perturbations and potential interactions with interstellar material. Such interactions may have contributed to the comet's current state, influencing its activity and potentially introducing new chemical signatures into its coma. The cumulative effect of these encounters over billions of years underscores the dynamic nature of interstellar space, where objects like 3I Atlas are continuously shaped by the gravitational and environmental influences of their surroundings. As 3I Atlas continues its journey through the solar system, its age and origins serve as a reminder of the interconnectedness of cosmic phenomena. The comet's passage through the inner solar system is not merely a fleeting event, but a bridge between the past and the present, linking the ancient history of the Milky Way to the present-day exploration of our own celestial neighborhood. The study of 3I Atlas's composition and trajectory has opened new avenues for understanding the formation and evolution of interstellar objects, offering insights into the processes that govern the dispersal of cometary material across the galaxy. The implications of 3I Atlas's age and origin extend beyond the realm of astronomy. If the comet is indeed a relic of a bygone era, it carries with it the potential to reveal the chemical and physical conditions of the early universe. The presence of organic compounds in its coma, for instance, raises intriguing possibilities regarding the distribution of prebiotic materials in interstellar space. Could 3I Atlas have played a role in seeding other planetary systems with the building blocks of life? While such questions remain speculative, the study of interstellar comets like 3I Atlas brings us one step closer to answering them. In the grand tapestry of the cosmos, 3I Atlas stands as a testament to the enduring legacy of interstellar travel. Its journey through the Milky Way, spanning billions of years, is a story of survival and transformation, a tale of a cosmic wanderer that has endured the trials of time and space to arrive at our doorstep. As astronomers continue to unravel the mysteries of 3I Atlas, they are not only uncovering the secrets of a single comet, but also gaining a deeper understanding of the universe itself. The study of interstellar objects is a window into the past, a means of tracing the origins of matter and energy across the vast expanse of the cosmos. And in the case of 3I Atlas, that window is wide open, inviting us to peer into the depths of time and space. The discovery of 3I Atlas has sparked a lively debate among astronomers, with most concluding that it is a natural interstellar comet, while a small but vocal group has raised provocative questions about its potential artificial origin. On 16 July 2025, astrophysicist Avi Loeb and his colleagues at the Initiative for Interstellar Studies published a paper on Archaeology, suggesting that 3I Atlas could be an extraterrestrial spacecraft. Their argument centered on several perceived anomalies: the comet's apparent size, its trajectory aligned with the solar system's ecliptic plane, and the lack of detectable chemical signatures typical of comets. Loeb and his team posited that these features, while unusual, could be indicative of an advanced technological artifact rather than a natural object. The idea that 3I Atlas might be an alien spacecraft was met with immediate skepticism from the broader astronomical community. Critics, including prominent researchers such as Chris Lintott and Darryl Seligman, argued that the evidence presented in Loeb's paper was speculative at best and lacked the robust empirical support necessary to substantiate such a claim. Seligman, who led one of the first published studies on 3I Atlas, emphasized that numerous telescopic observations had clearly demonstrated the comet's cometary activity, including the outgassing of carbon dioxide, water, and carbon monoxide. These findings, he noted, were consistent with the behavior of natural comets and provided no indication of artificial construction. One of the key points of contention revolved around the detection, or lack thereof, of certain chemical compounds in 3I Atlas's Coma. Loeb's team argued that the absence of identifiable chemicals, such as diatomic carbon, CO₂, and tricarbon, might, however, astronomers quickly countered that the absence of these compounds was not necessarily anomalous. Observations by the MDM Observatory and other facilities had failed to detect CO₂ and C3 in 3I Atlas's Coma, which is consistent with the object's high depletion in carbon chain compounds. In fact, 3I Atlas was found to be one of the most carbon chain depleted comets ever observed, a feature that could be explained by its unique composition or the conditions under which it formed. Another point of debate centered on the comet's trajectory. Loeb and his colleagues noted that 3I Atlas's path was aligned with the ecliptic plane, the orbital plane shared by the planets of the solar system. This alignment, they argued, was statistically improbable for a random interstellar object and could suggest intentional targeting. However, astronomers such as Scott Manley and David Kipping challenged this interpretation, highlighting that the alignment of 3I Atlas with the ecliptic could be a result of gravitational interactions within the Milky Way. The thick disk, from which 3I Atlas is believed to originate, has a different orientation relative to the galactic plane, and the comet's trajectory could have been subtly influenced by the gravitational pull of nearby stars or interstellar clouds. These factors, they argued, provided a natural explanation for the observed trajectory, without invoking the need for artificial intervention. Perhaps the most compelling rebuttal to Loeb's hypothesis came from the detection of nickel and cyanide in 3I Atlas's Coma. These substances, while unusual in their relative abundance, are commonly found in comets and are not indicative of artificial construction. The Very Large Telescope VLT observed a steady increase in the concentration of nickel and cyanide as 3I Atlas approached the Sun, a pattern consistent with the outgassing of volatile materials from a natural comet. The presence of atomic nickel vapor, in particular, was cited as evidence of the comet's natural origin, as it aligns with the chemical processes observed in other comets. While the absence of detectable iron vapor was noted, astronomers explained that this discrepancy could be due to the selective release of nickel through the decomposition of nickel-containing organic compounds, a process that is well documented in cometary chemistry, despite the overwhelming consensus among astronomers that 3I Atlas is a natural interstellar comet. Loeb and his team maintained that their hypothesis was worth exploring as a thought experiment. In a blog post, Loeb acknowledged that the likelihood of 3I Atlas being an artificial object was low, but emphasized the importance of remaining open-minded in the face of the unknown. He argued that extraordinary claims require extraordinary evidence, and while the evidence presented in his paper fell short of that threshold, the exercise of considering alternative explanations was a valuable contribution to the scientific discourse. The debate over 3I Atlas ultimately underscored the importance of rigorous scientific inquiry and the need to balance curiosity with critical thinking. While the hypothesis of an alien spacecraft may capture the imagination, the overwhelming weight of observational evidence supports the conclusion that 3I Atlas is a natural interstellar comet. The study of such objects continues to yield valuable insights into the formation and evolution of planetary systems, as well as the dynamic processes that govern the Milky Way. As 3I Atlas continues its journey through the solar system, it serves as a reminder that the universe is full of mysteries waiting to be unraveled, not through speculation, but through careful observation and the relentless pursuit of knowledge. As 3I Atlas continues its trajectory through the solar system, its passage offers more than just a fleeting glimpse of an interstellar traveler. It presents a unique opportunity to refine our strategies for future interstellar exploration. The study of this comet has already expanded our understanding of the chemical diversity of interstellar objects and the conditions under which they form. However, the true value of 3I Atlas lies in the lessons it imparts for the design and execution of future missions aimed at studying interstellar visitors. The challenges posed by 3I Atlas, from its high velocity to its distant point of origin, highlight the need for innovative propulsion technologies and advanced observational techniques capable of tracking and analyzing such objects in real time. One of the most pressing challenges in planning a mission to an interstellar object is the sheer speed at which these bodies travel. 3I Atlas, for instance, is moving at a hyperbolic excess velocity of 58 kilometers per second, significantly faster than the previous interstellar visitors, 1I Oumuamua and 2I Borisov. Launching a spacecraft from Earth to intercept such an object would require an enormous amount of energy, as any post-discovery mission would need to achieve a delta V, change in velocity of at least 24 kilometers per second, well beyond the capabilities of current propulsion systems. Even if 3I Atlas had been discovered earlier, a mission launched from Earth would still require a substantial amount of fuel to match the comet's velocity and trajectory. This challenge underscores the need for developing advanced propulsion technologies, such as nuclear thermal propulsion or solar sails, which could enable faster and more efficient interstellar missions. Given the difficulties of launching from Earth, some researchers have proposed that future missions to interstellar objects could originate from Mars or other locations within the solar system. AMPA's July 2025 study, led by Atsuhiro Yaginuma and collaborators, suggested that launching a spacecraft from Mars could reduce the required delta V to around 5 kilometers per second, making it a more feasible option for intercepting an interstellar object like 3I Atlas. This approach would leverage Mars's lower gravity and strategic position in the solar system, potentially allowing for a more energy-efficient trajectory to an approaching interstellar visitor. Moreover, the presence of robotic spacecraft such as the Juno mission orbiting Jupiter and the Cycle and JUICE missions traveling through the outer solar system opens the possibility of repurposing existing assets to observe interstellar objects as they pass by. While redirecting these spacecraft to intercept 3I Atlas may not be practical due to fuel and mission constraints, their ability to observe the comet from a vantage point outside Earth's orbit provides valuable data that enhances our understanding of its behavior and composition. Beyond propulsion and mission design, The study of 3I Atlas also highlights the importance of early detection and rapid response capabilities. The comet's initial discovery by the Atlas survey was followed by swift follow-up observations from a global network of telescopes, enabling astronomers to refine its trajectory and determine its interstellar nature. However, the fact that 3I Atlas was not detected earlier, despite being observed by the Zwicky Transient Facility and the Vera C. Rubin Observatory in the weeks preceding its official discovery, raises concerns about the limitations of current detection systems. The comet's proximity to the galactic center, a region densely populated with stars, made it difficult to distinguish from background objects. Future interstellar object detection efforts must therefore prioritize improving observational coverage in such challenging regions and developing algorithms capable of identifying faint, fast-moving objects against crowded stellar fields. The development of next-generation telescopes and space-based observatories will also play a crucial role in enhancing our ability to study interstellar objects. The James Webb Space Telescope and the upcoming Nancy Grace Roman Space Telescope have already demonstrated their utility in analyzing the composition of 3I Atlas, detecting the presence of carbon dioxide, water ice, and other volatile compounds. As these instruments continue to operate and newer facilities come online, they will enable more detailed spectroscopic analyses of interstellar visitors, shedding light on their chemical makeup and evolutionary history. Additionally, the deployment of dedicated interstellar object observatories, such as the proposed Interstellar Mapping and Acceleration Probe mission (IMAP), could provide continuous monitoring of the heliosphere and improve our chances of detecting and characterizing interstellar objects before they reach the inner solar system. While the immediate prospects for sending a spacecraft to intercept 3I Atlas remain limited, the comet's passage serves as a blueprint for future interstellar missions. The data gathered from this event will inform the design of specialized spacecraft equipped with advanced instrumentation, such as mass spectrometers, dust analyzers, and remote sensing tools, capable of studying interstellar objects in unprecedented detail. These missions could provide insights into the formation of planetary systems beyond our own, the distribution of organic materials in the galaxy, and the potential for life-supporting chemistry in interstellar space. Ultimately, the study of 3I Atlas is not just about understanding a single comet. It is about preparing for a future in which humanity extends its reach beyond the boundaries of the solar system. As 3I Atlas continues its journey through the cosmos, it leaves behind a trail of knowledge and inspiration. The questions it raises about the origins of interstellar objects, the mechanisms by which they are ejected from their parent star systems, and the role they play in the broader galactic ecosystem, are just beginning to be explored. The next chapter in the story of interstellar exploration will be written by the technologies and strategies we develop in the coming decades, guided by the lessons learned from 3I Atlas and the countless other interstellar visitors that will inevitably cross our cosmic path. The universe is vast, and our journey to understand it has only just begun. In the vast tapestry of the cosmos, where stars burn like ancient sentinels and galaxies spiral in eternal waltz, the arrival of 3I Atlas is a whisper of the universe's boundless expanse. Discovered in the quiet Chilean desert, under the watchful gaze of the Atlas telescope, this interstellar comet hurtles through the solar system at a blistering 58 kilometers per second, a speed so great it defies the sun's gravitational embrace. Its path, a razor-sharp arc bending through the inner solar system, is not a loop of return but a fleeting visit, a hyperbolic trajectory that marks it as a traveler from elsewhere. Yet, what makes this path so extraordinary? Why does 3I Atlas move like a phantom, unshackled by the laws that bind planets and asteroids to their orbits? To unravel this mystery, we must peer into the fundamental forces that sculpt the heavens: gravity and velocity. The comet's journey is a testament to the delicate balance between these forces. While planets orbit the sun in elliptical loops, tethered by gravity's invisible thread, 3I Atlas moves on a path that curves away forever. Its hyperbolic orbit, a mathematical curve stretching infinitely outward, is a signature of escape. The sun's pull, though immense, cannot slow it enough to trap it in a cycle of return. Instead, 3I Atlas borrows energy from the solar system, flinging itself back into the interstellar void, a relic of another star's history now passing through ours. This chapter explores the physics that define such trajectories, the cosmic rules that govern the fate of interstellar wanderers, and the profound questions they raise about our place in the galaxy. At the heart of 3I Atlas's journey lies a concept both elegant and brutal: escape velocity. Every celestial body, from Earth to the Sun, exerts a gravitational pull that seeks to bind objects to its orbit. To break free, an object must achieve a speed sufficient to overcome this pull. For the Sun, this threshold, the escape velocity, is approximately 617 kilometers per second. Yet 3I Atlas arrives with a velocity of 58 kilometers per second relative to the Sun, a fraction of this threshold. How then does it escape? The answer lies in the comet's hyperbolic trajectory. Orbital mechanics reveals that an object's path is determined by its energy and angular momentum. In the case of 3I Atlas, its kinetic energy derived from its speed exceeds the gravitational potential energy binding it to the Sun. This imbalance creates a hyperbolic orbit characterized by an eccentricity, measures the deviation of an orbit from a perfect circle, with E0 denoting a circular orbit and E1 describing an ellipse. For 3I Atlas, E6.141, a number so extreme that its trajectory appears almost straight line in the vastness of space. What distinguishes 3I Atlas from the elliptical paths of planets and comets native to the solar system? The key lies in its velocity vector. While planets and asteroids are gravitationally bound, their velocities are insufficient to escape the Sun's influence. 3I Atlas, however, carries the imprint of a different gravitational history. Its speed is not self-generated, but inherited from the chaotic dance of its origin system. Perhaps it was hurled into the void by the gravitational slingshot of a massive planet, or the tidal forces of a passing star. Whatever the mechanism, its velocity ensures it will never return to the Sun. The comet's hyperbolic excess velocity, Vn, of 58 kilometers per second, further underscores its interstellar provenance. This speed, measured relative to the Sun, represents the comet's velocity at an infinite distance from the solar system. For comparison, the previous interstellar visitors, 1I Oumuamua, Vn, 26 kilometers per second, and 2I Borisov, Vn, 32 kilometers per second, moved at more moderate paces. 3I Atlas's blistering speed suggests it may have originated from a more distant or dynamically active region of the galaxy, where gravitational interactions are more violent. This trajectory is not random. It is a consequence of the comet's velocity and the Sun's gravity working in tandem. As 3I Atlas approaches the Sun, it accelerates, reaching a peak speed of 68 kilometers per second at perihelion. Yet, as it departs, the Sun's gravity slows it only marginally, leaving it with enough residual velocity to escape. The result is a trajectory that arcs sharply through the inner solar system before vanishing into the dark, a ghostly echo of a star system we will never see. The hyperbolic path of 3I Atlas is more than a mathematical curiosity. It is a window into the dynamics of interstellar travel. Unlike comets born in the Oort cloud or Kuiper belt, which are loosely bound to the solar system and occasionally nudged inward by gravitational perturbations, 3I Atlas is a true interloper. Its trajectory tells a story of ejection, a violent expulsion from its home system. The question is, how did it arrive here? The most plausible explanation is gravitational scattering. In the tumultuous cradles of star-forming regions, where young planetary systems are still coalescing, gravitational interactions between planets and passing stars can hurl objects into the void. Amper's giant planet, for instance, could gravitationally slingshot 3I Atlas into interstellar space, much like a stone flung from a sling. Similarly, the passage of a rogue star or a dense molecular cloud could disrupt the comet's orbit, sending it careening into the galaxy. Once adrift, 3I Atlas would drift through the interstellar medium for eons, its path determined by the faint gravitational tugs of distant stars and the galactic tide. The comet's trajectory also offers clues about its origin. By tracing its path backward in time, astronomers have determined that 3I Atlas approached the solar system from the direction of the constellation Sagittarius, near the Milky Way's galactic center. However, unlike the first two interstellar objects which hailed from the northern celestial hemisphere, 3I Atlas originates from the south, a region less studied due to the dense star fields of the galactic plane. This southern origin challenges assumptions about the distribution of interstellar objects, suggesting that our telescopes may have missed many such travelers. Moreover, 3I Atlas's vertical velocity component, watts 1018.5 kilometers per second, indicates it belongs to the Milky Way's thick disk population, a group of older stars with higher galactic altitudes and lower metallicity. If this classification holds, the comet could be up to 14 billion years old, older than the solar system itself. Such an age would make it a relic from the early days of the galaxy, a time when star formation was more frenetic and planetary systems were more chaotic. Studying 3I Atlas's composition therefore could offer insights into the primordial building blocks of planets in the Milky Way's youth. Yet the comet's journey is not without peril. As it traverses the inner solar system, it will pass within 0.19 AU of Mars and 0.36 AU of Jupiter. These close encounters, while not threatening to Earth, will subject the comet to gravitational tugs that could subtly alter its trajectory. Jupiter in particular may exert a measurable influence, either accelerating or decelerating the comet as it swings by. These interactions are a reminder that even interstellar travelers are not entirely free from the gravitational web of the galaxy. The hyperbolic orbit of 3I Atlas also raises philosophical questions. What does it mean to be unbound? In the grand scale of the cosmos, 3I Atlas is both solitary and connected, a fragment of a distant star system now weaving through ours. Its path is a bridge between worlds, a testament to the fluidity of cosmic history. Yet its escape velocity ensures it will leave no trace of its passage, save for the fleeting light it casts upon our telescopes. As 3I Atlas continues its flight through the solar system, its hyperbolic orbit serves as a Rosetta Stone, decoding the forces that govern interstellar travel. Yet this trajectory is only one piece of a larger puzzle. To understand the comet's true story, we must look beyond its path and into the galactic neighborhood from which it came. The next chapter will explore the origins of 3I Atlas, delving into the structure of the Milky Way, the age of the comet, and the enigmatic parent star that may have birthed it. By piecing together these clues, we hope to answer a question as ancient as the stars themselves. Where do we come from, and where are we going? In the vast, uncharted expanse of the cosmos, where galaxies spiral like celestial whirlpools and stars burn in silent symphony, a traveler from another corner of the Milky Way has arrived. Discovered on 1 July 2025 by the Atlas telescope in Chile, 3I Atlas, a comet born among the stars of a distant stellar nursery, has embarked on a fleeting passage through our solar system. Its arrival is not accidental. This interstellar wanderer, the third such object ever identified, carries secrets of a primordial era etched into its icy nucleus and trailing clouds of gas and dust. As it glides past the sun, 3I Atlas becomes a cosmic messenger, whispering tales of its birthplace in the galactic depths. Yet, 3I Atlas is not merely a visitor. Its trajectory, a hyperbolic arc unbound by the sun's gravity, reveals a velocity of 58 kilometers per second, a speed that defies the gravitational embrace of our solar system. It arrives from the direction of Sagittarius, near the heart of the Milky Way, and will depart just as swiftly, vanishing into the void. But its journey is far from simple. The comet's origin, its age, and its composition challenge our understanding of the universe. Is 3I Atlas a relic from the early Milky Way, older than the solar system itself? What can its chemistry tell us about the conditions of its birthplace? And how does its existence reshape our view of the cosmos as a dynamic, interconnected web of celestial bodies? As we trace the comet's path, we are drawn into a story of cosmic migration, galactic history, and the enduring mystery of our place in the universe. 3I Atlas is more than a passing phenomenon. It is a window into the ancient past, a testament to the vastness of time and space, and a reminder that we are not alone in the dark. To understand 3I Atlas's significance, we must first grasp the nature of its journey. Unlike the familiar comets of the solar system, which orbit the Sun in elliptical paths, 3I Atlas follows a hyperbolic trajectory. This means it is not gravitationally bound to the Sun and will escape the solar system entirely. Its hyperbolic excess velocity, the speed it possesses beyond what the Sun's gravity could provide, is a staggering 58 kilometers per second. For context, this is nearly double the speed of the previous interstellar object, 2I Borisov, and over twice that of 1I Oumuamua. Such a velocity implies that 3I Atlas has not originated from within the solar system, but has traveled from another star system, carried by the gravitational tides of the galaxy itself. The comet's trajectory is defined by an orbital eccentricity of 6.141, a value far exceeding the 1.0 threshold that separates closed elliptical orbits from open, hyperbolic ones. This extreme eccentricity gives 3I Atlas's path a nearly straight-line appearance, a stark contrast to the curved orbits of native comets. Its closest approach to the Sun, perihelion, will occur on 29 October 2025 at a distance of 1.36 AU, placing it between Earth and Mars. Yet despite its proximity to the inner solar system, 3I Atlas will never pose a threat to Earth, remaining at least 1.8 AU away. What sets 3I Atlas apart is not just its speed, but its origin. By tracing its trajectory backward in time, astronomers have determined that the comet entered the solar system from the direction of the Milky Way's galactic center. However, its origin is not as straightforward as it seems. The comet's velocity components, its motion relative to the galactic plane and the Sun, suggest a connection to the Milky Way's thick disk, a population of older stars with lower metallicity, abundance of elements heavier than helium. This places 3I Atlas in a category of objects that may predate the solar system, potentially dating back 7 to 14 billion years. The discovery of 3I Atlas raises profound questions. How does a comet endure billions of years of galactic travel without being destroyed? What processes in its parent star system propelled it into interstellar space? And how do its chemical signatures, unlike those of solar system comets, reflect the conditions of its birthplace? To answer these questions, we must delve deeper into the comet's physical characteristics and the enigma of its ancient provenance. The composition of 3I Atlas offers tantalizing clues about its origin. Observations by the James Webb Space Telescope, JWST, and the SPHEREX mission reveal an unusual richness in carbon dioxide, CO2, with a CO2 to water ratio 8 times higher than typical solar system comets. This anomaly suggests that 3I Atlas formed in a region where temperatures were low enough for CO2 to freeze, a condition that occurs far from a star, beyond the CO2 frost line in its parent star system. Such an environment is rare in the solar system, where most comets originate in the Kuiper belt or the distant Oort cloud, where water ice dominates. Moreover, 3I Atlas's Coma contains traces of water ice, carbon monoxide, and carbonyl sulfide, but lacks the carbon chain compounds, like C2 and C3, that are common in solar system comets. This depletion hints at a unique chemical history, possibly shaped by the low metallicity environment of the thick disk. The absence of iron vapor, despite the detection of atomic nickel, further distinguishes 3I Atlas from its solar system counterparts. These findings challenge existing models of comet formation and suggest that the comet's parent star system was chemically distinct from our own. Perhaps the most astonishing revelation is the age of 3I Atlas. If it indeed belongs to the thick disk population, its estimated age of 7 to 14 billion years surpasses the 4.6 billion-year-old solar system by millions to billions of years. Such an ancient origin implies that 3I Atlas predates the formation of our planetary neighborhood and may have witnessed the violent collisions and mergers that shaped the Milky Way. Its survival over eons is a testament to the resilience of cometary nuclei, which can endure in the frozen vaults of interstellar space until gravitational perturbations send them hurtling into new realms. The implications of 3I Atlas's age and composition extend beyond astronomy. If the comet retains material from the early Milky Way, it could serve as a time capsule, preserving the chemical fingerprints of a bygone era. The detection of heavy isotopes like carbon-13 in its CO₂ molecules may offer insights into the nucleosynthetic processes of ancient stars, while the absence of certain organic compounds could shed light on the conditions necessary for life's precursors to form. In essence, 3I Atlas is not just a comet, it is a Rosetta Stone for understanding the evolution of galaxies and the cosmic recipe for life. Yet the question remains, how did a comet as old as 3I Atlas endure the tumultuous journey through the Milky Way? For billions of years, it has traversed the galaxy, encountering the gravitational tides of stars, the shockwaves of supernovae, and the silent pull of dark matter. Its survival is a puzzle, one that may be solved by studying the dynamics of interstellar space. Did 3I Atlas originate in a binary star system, where gravitational interactions ejected it into the void? Or was it flung from its birthplace by the explosive death of its parent star? The answer lies in the comet's velocity vector. Its retrograde motion, traveling in the opposite direction to the Milky Way's rotation, and its high vertical velocity, Watts plus 18.5 kilometers per second, indicate that it does not belong to the orderly plane of the thin disk, but instead hails from the chaotic thick disk. Here, stars move in random, tilted orbits, and comets like 3I Atlas may have been scattered into interstellar space by the gravitational chaos of a dying planetary system. Over time, the comet's trajectory would have been further altered by encounters with rogue planets, molecular clouds, and even the supermassive black hole at the galactic center. As 3I Atlas continues its journey, it will serve as a beacon for future discoveries. Its passage through the solar system has already demonstrated the power of modern telescopes to unravel the mysteries of interstellar objects. The data collected by Hubble, JWST, and ground-based observatories will refine our understanding of comet formation, galactic dynamics, and the chemical diversity of the cosmos. But 3I Atlas is just the beginning. With instruments like the Vera C. Rubin Observatory scanning the skies, we may soon find more interstellar travelers, each carrying their own stories of distant stars and forgotten worlds. And so, as 3I Atlas departs our solar system, it leaves behind a trail of questions as luminous as its Coma. What other secrets lie buried in the ice of interstellar comets? What other ancient messengers await discovery in the dark? Perhaps, in the vast silence of space, we are not alone, but rather part of a grander interconnected tapestry of cosmic life. What if 3I Atlas's journey was not entirely its own? What if, in the vast emptiness of interstellar space, it brushed against the gravitational shadow of a silent giant, a rogue planet, untethered to any star, adrift in the cosmic dark? Rogue planets, those enigmatic wanderers of the galaxy, drift unseen through the void, their origins shrouded in mystery. Unlike stars, which blaze with nuclear fire, or even the comets and asteroids that orbit the sun, these objects exist in a state of perpetual homelessness, unanchored to any system. Could one of these phantom hitchhikers have nudged 3I Atlas into its hyperbolic path? The idea is tantalizing, a reminder that the universe is not merely a backdrop for celestial bodies, but a dynamic arena where gravity weaves stories of collision and escape. To understand 3I Atlas fully, we must venture beyond its immediate properties and consider the possibility that its trajectory, a seemingly straight line through the solar system, might bear the subtle imprint of a rogue planet's touch. Rogue planets are born like all other planets, within the swirling disks of gas and dust that surround young stars, but their fates diverge dramatically. Through violent gravitational interactions with sibling planets or passing stars, they are cast out from their nurseries, flung into the interstellar abyss. These exiles are not mere theoretical constructs. Their existence is inferred from indirect evidence, such as the micro-lensing of distant stars and the peculiar motions of objects in the outer solar system. Estimates suggest that the Milky Way harbors billions of rogue planets, some the size of Earth, others as massive as Jupiter, yet they remain invisible to our telescopes. detectable only through their fleeting gravitational effects. When considering 3I Atlas's journey, the role of rogue planets becomes a compelling hypothesis. Simulations of its trajectory reveal that the comet has passed within 1 parsec, approximately 3.3 light-years, of 25 known stars over the past 10 million years. Such proximity increases the likelihood of gravitational encounters, even with objects as faint as rogue planets. These interactions could alter a comet's path, accelerating it or redirecting it toward a new destination. For 3I Atlas, which travels at a hyperbolic excess velocity of 58 kilometers per second, far faster than the average of interstellar objects like 1I Oumuamua and 2I Borisov, the question arises, did a rogue planet provide the final push to send it hurtling through the solar system? The mechanics of such an encounter are intricate. AMPA's rogue planet, drifting silently through the galaxy, could intersect 3I Atlas's orbit at just the right angle and velocity to impart a significant change in momentum. If 3I Atlas originated in the thick disk of the Milky Way, a region populated by older stars and potentially more rogue planets, the probability of such an interaction increases. Moreover, the high vertical velocity component of 3I Atlas's trajectory, its movement perpendicular to the galactic plane, suggests it may have originated from a population of stars or objects with distinct kinematics, possibly influenced by gravitational perturbations from rogue planets. If a rogue planet did shape 3I Atlas's journey, what does this imply about the comet's origin and evolution? Rogue planets are often ejected from systems where they formed, carrying with them the chemical signatures of their birthplaces. If 3I Atlas interacted with such a world, it might have acquired traces of its environment, subtly altering its composition or trajectory. For instance, a rogue planet's gravity could have stripped material from 3I Atlas's nucleus or Coma, leaving behind clues about their encounter. Alternatively, the comet's unusual richness in carbon dioxide, as observed by the James Webb Space Telescope, might hint at a formation region influenced by the same conditions that produce rogue planets: cold, isolated, and rich in volatile ices. The implications extend beyond 3I Atlas. Rogue planets, though elusive, are believed to be common in the galaxy. Their gravitational influence could shape the distribution of interstellar objects, redirecting them towards stars like the Sun, or scattering them into the depths of space. Understanding how these invisible giants interact with comets and asteroids could refine our models of galactic dynamics and shed light on the chaotic processes that govern planetary systems. Furthermore, detecting rogue planets remains a challenge, but their gravitational fingerprints on objects like 3I Atlas offer a potential roadmap. By studying the trajectories of interstellar visitors, astronomers might piece together the hidden architecture of the galaxy, revealing the unseen forces that sculpt the cosmos. Yet the search for rogue planets is fraught with uncertainty. Their detection relies on indirect methods, and even when observed, their properties remain largely speculative. Could 3I Atlas's path be a natural consequence of its birthplace in the thick disk, or does it bear the mark of a rogue planet's touch? The answer may lie in future observations of the comet as it exits the solar system. By tracking its precise trajectory and analyzing the subtle deviations caused by gravitational interactions, scientists might uncover evidence of a rogue planet's influence. Until then, 3I Atlas serves as a cosmic puzzle, a testament to the unseen forces that govern the universe. But if rogue planets are the silent giants of the interstellar void, there exists an even more formidable force: black holes. These cosmic behemoths, with their gravitational pulls so intense that not even light can escape, are the ultimate arbiters of fate in the universe. While 3I Atlas's journey may have skirted the edges of gravitational chaos, black holes represent a deeper mystery, one where space and time themselves bend and twist under their influence. Just as rogue planets could nudge a comet off course, black holes might warp the fabric of reality, leaving indelible marks on the paths of interstellar travelers. As we turn our gaze to these enigmatic entities, we step further into the heart of the universe's most profound secrets. Imagine a region of space where gravity is so absolute that nothing, not matter, not energy, not even light, can flee its grasp. AMPA's black hole. is not merely a void in the cosmos. It is a boundary between what we know and what lies beyond, a point of no return that defies intuition. While 3I Atlas's journey through the solar system was shaped by the gentle nudges of rogue planets and the gravitational dance of stars, black holes operate on a scale of destruction and creation. These objects, born from the collapse of massive stars, are the ultimate gatekeepers of the universe, their event horizons marking the edge of our comprehension. Could a black hole have played a role in shaping 3I Atlas's trajectory, or perhaps even in the formation of the comet itself? The idea is as unsettling as it is fascinating. A reminder that the cosmos is a realm of extremes. Black holes come in many forms, from the stellar mass remnants of supernovae to supermassive behemoths that anchor the centers of galaxies. At their core is the singularity, a point of infinite density where the laws of physics as we know them break down. Surrounding the singularity is the event horizon, the threshold beyond which escape is impossible. For 3I Atlas, a black hole's influence would manifest not in direct contact, but in the subtle warping of space-time. If the comet had ventured too close to one, its trajectory would have been irrevocably altered, either flung into a new orbit or swallowed whole. Yet black holes are not merely destructive. Their gravitational fields can act as slingshots, accelerating objects to relativistic speeds through a process called gravitational lensing. If 3I Atlas had passed near a black hole in its distant past, it might have been hurled toward the solar system with the velocity it now carries. Theoretical models suggest that interstellar objects like 3I Atlas could originate from the outer reaches of the galaxy, where the gravitational tides of supermassive black holes stir the interstellar medium into chaos. In such regions, comets and asteroids might be ejected from their homes, propelled into the void by the black hole's relentless pull. Moreover, black holes are not static. They interact with their environments, accreting matter and releasing torrents of energy in the form of jets and radiation. These processes could influence the chemistry of nearby objects, subjecting them to extreme conditions. If 3I Atlas had traversed a region near a black hole, it might have been bombarded by high-energy particles or exposed to intense magnetic fields, altering its composition in ways yet to be understood. The presence of heavy elements like nickel in its coma, for instance, could hint at an origin in a region where stellar death and rebirth occur frequently. Near the galactic center, where black holes reign supreme, the implications of a black hole's influence on 3I Atlas are profound. If the comet's trajectory bears the imprint of a black hole's gravity, it would suggest that such objects play a more active role in shaping the interstellar medium than previously thought. Rather than existing as isolated singularities, black holes might be cosmic architects, sculpting the distribution of matter and energy across the galaxy. For 3I Atlas, this could mean that its journey is not random, but part of a grander pattern, a thread in the tapestry woven by the gravitational forces of the Milky Way. Furthermore, the study of 3I Atlas offers a unique opportunity to test the boundaries of our understanding. By analyzing its trajectory and composition, astronomers might identify subtle anomalies that could only be explained by the influence of a black hole. For example, a deviation in its path that cannot be attributed to known stars or rogue planets might hint at a past encounter with an unseen gravitational force. Similarly, the detection of exotic elements or isotopes in its coma could provide clues about its exposure to the extreme environments near a black hole. Yet the role of black holes in 3I Atlas's story is not without controversy. Critics argue that the comet's relatively modest velocity and trajectory make a direct interaction with a black hole unlikely. The Milky Way's supermassive black hole, Sagittarius Ampères, lies at the galactic center, a region far removed from 3I Atlas's origin in the thick disk. Stellar mass black holes, while more common, are still rare enough that the probability of 3I Atlas encountering one is low. However, the universe is vast and unpredictable, and the possibility remains that a black hole's gravitational footprint could be hidden in the comet's path, waiting to be deciphered. While black holes loom as titanic sentinels in the cosmic landscape, there exists another force that shapes the universe on a subtler scale: dark matter. Invisible and intangible, Dark matter permeates the cosmos, its gravitational influence binding galaxies together and dictating the motion of stars. If 3I Atlas's journey was guided by the unseen hand of rogue planets or the inexorable pull of black holes, it may also be dancing to the rhythm of dark matter. This mysterious substance, which constitutes 85% of the universe's mass, is the final frontier in our quest to understand the cosmos. As we turn our attention to dark matter, we step into a realm where the known laws of physics falter and the universe reveals its deepest secrets. Beneath the vast velvet expanse of the night sky, where stars flicker like ancient sentinels, a silent traveler glides through the solar system, discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, ATLAS, at Rio Hurtado, Chile. 3I Atlas, a comet born beyond our cosmic neighborhood, has ignited the imagination of astronomers and dreamers alike. This interstellar wanderer, the third such object to be confirmed in human history, carries secrets etched in the primordial dust of distant star systems. Its arrival is not a mere celestial event, but a whisper from the cosmos, a reminder that we are but one thread in the infinite tapestry of the universe. 3I Atlas's journey began long before its detection, traversing the void of interstellar space for untold millennia. Its hyperbolic trajectory, a path too swift to be bound by the sun's gravity, marks it as an outsider, unlike the asteroids and comets native to the solar system, which orbit in predictable loops. 3I Atlas hurtles through our backyard at a blistering speed of 58 kilometers per second, over 130,000 miles per hour. Yet this comet is no harbinger of doom. It will never come closer than 1.8 AU, 270 million kilometers to Earth, a distance that ensures humanity's safety while allowing us to study it in awe. What makes 3I Atlas extraordinary is not merely its origin, but its composition. Telescopes have revealed a coma rich in carbon dioxide, water vapor, and traces of cyanide and nickel chemical fingerprints that hint at its birthplace in the frigid outskirts of another star system. These discoveries challenge our understanding of planetary formation and offer a glimpse into the chaotic nurseries where stars and worlds are born. As we peer at 3I Atlas through instruments like the James Webb Space Telescope, we are not just observing a comet. We are deciphering a message from the furthest reaches of the galaxy, carried on a fragile, icy nucleus. In the grand theater of the cosmos, 3I Atlas is both a protagonist and a witness. Its passage through the solar system is a fleeting moment in the universe's eternal timeline, yet it compels us to ask profound questions. How many such travelers have passed unnoticed? What stories do they carry from the dark corners of space? And what might they teach us about the origins of life, the structure of galaxies, and our place in the universe? To understand 3I Atlas's journey, we must first unravel the physics that govern its trajectory. The comet's hyperbolic path, a curve that diverges infinitely from the sun, is a testament to its interstellar heritage. Unlike elliptical orbits, which loop back to their starting points, a hyperbolic trajectory is a one-way ticket. The sun's gravity, though immense, cannot capture 3I Atlas. It is moving too fast. This velocity, known as the hyperbolic excess velocity (via), is the comet's speed relative to the sun after accounting for the gravitational pull that accelerates it as it approaches. For 3I Atlas, this via is 58 kilometers per second, a staggering figure that dwarfs the velocities of the two previously discovered interstellar objects, 1I Oumuamua, 26 kilometers per second, and 2I Borisov, 32 kilometers per second. This speed is not random. It is a relic of 3I Atlas's origin in the Milky Way. To trace its path backward in time, astronomers analyze the comet's orbital eccentricity, a measure of how elongated its orbit is, with an eccentricity of 6.141. 3I Atlas's trajectory is the most extreme of any interstellar object yet observed. Such a value implies that the comet's path is nearly straight, a consequence of its high velocity and the weak gravitational influence of the solar system. By calculating the comet's position and velocity at the time of discovery, scientists have determined that it originated from the direction of the galactic center, near the constellation Sagittarius. This region, teeming with stars and dark matter, is a crucible of stellar births and deaths, where comets like 3I Atlas might have been ejected from their home systems by gravitational interactions with massive stars or planets. The comet's journey is also marked by encounters with the planets of the solar system. Though it will not collide with any, its path brings it within striking distance of Mars, Venus, and Jupiter. On 3 October 2025, 3I Atlas will pass 0.19 AU from Mars, a distance close enough for Martian orbiters to capture images of the comet as it brightens. Later, on 3 November 2025, it will brush past Venus at 0.65 AU, and on 16 March 2026, it will swing within 0.36 AU of Jupiter. These encounters, while not altering the comet's trajectory significantly, offer opportunities to study how interstellar objects interact with the gravitational forces of our planetary system. Yet the true marvel of 3I Atlas lies in its survival. The comet's nucleus, estimated to be less than 1 kilometer in diameter, is a fragile relic of its past. As it approaches the sun, the nucleus heats up, sublimating its ices into gas and dust that form the coma. This process, driven by solar radiation, is both a source of beauty and a harbinger of destruction. The comet's CO₂-rich coma, detected by the James Webb Space Telescope, suggests that it formed in a region where temperatures were cold enough for carbon dioxide to freeze. Such conditions exist beyond the CO₂ frost line, in protoplanetary disks, the swirling clouds of gas and dust that surround young stars. By studying the composition of 3I Atlas, astronomers hope to reconstruct the environment of its birthplace, shedding light on the diversity of planetary systems across the galaxy. The comet's trajectory and composition are not just scientific curiosities, they are clues to the dynamic history of the Milky Way. The fact that 3I Atlas hails from the southern celestial hemisphere, a region less frequently observed due to the dense star fields of the galactic center, challenges assumptions about the distribution of interstellar objects. Previous theories predicted that more interstellar visitors would originate from the solar apex, the direction in which the sun is moving relative to nearby stars. Instead, 3I Atlas's southern origin suggests that our view of the cosmos is incomplete, and that many more interstellar travelers may lurk undetected in the dark. As 3I Atlas continues its journey, it serves as a bridge between the familiar and the unknown. Its hyperbolic path is a reminder that the universe is not static, but in constant motion, a dance of gravity and chaos that shapes the destinies of stars and worlds. By unraveling the mysteries of 3I Atlas, we gain not only knowledge of a single comet, but a deeper understanding of the forces that govern the cosmos. If 3I Atlas is a messenger from the stars, then its age is the seal of its origin. Studies of its trajectory and motion suggest that this comet is not merely ancient but possibly older than the solar system itself. By analyzing its velocity components, how it moves relative to the Milky Way, astronomers have determined that 3I Atlas belongs to either the thin or thick disk population of the galaxy. The thick disk, a region populated by stars that formed billions of years ago, holds clues to the galaxy's earliest days. If 3I Atlas is indeed a member of this population, its age could range from 7.6 to 14 billion years, placing it in an era when the Milky Way was still coalescing from primordial gas. This staggering antiquity raises profound questions about the comet's history. How did it survive for so long, enduring the tumult of stellar collisions, supernovae, and the gravitational tides of the galaxy? The answer may lie in its composition. The high concentration of carbon dioxide in 3I Atlas's Coma, detected by the James Webb Space Telescope, hints at a formation process unlike that of solar system comets. While comets in our neighborhood often contain water ice as their dominant volatile, 3I Atlas's CO₂-rich profile suggests it formed in a colder, more distant region of its parent system. Such conditions would have shielded the comet from the violent processes that might otherwise have destroyed it, allowing it to endure as a relic of a bygone epoch. Yet the comet's journey has not been solitary. Over the past 10 million years, 3I Atlas may have passed within 1 parsec, 3.3 light-years, of 25 known stars, each encounter nudging its trajectory and altering its velocity. These gravitational slingshots, akin to cosmic billiards, have sculpted the comet's path across the galaxy. One particularly intriguing possibility is that 3I Atlas once orbited a star in the thick disk, only to be ejected by the gravitational influence of a passing giant planet or a binary companion. Such ejections are common in young star systems, where planets and comets jostle for stability. By studying 3I Atlas, we gain insight into the chaotic youth of distant worlds, a process that may mirror the early history of our own solar system. The comet's survival is also a testament to the resilience of interstellar objects. Despite its fragility, 3I Atlas has withstood the rigors of deep space, its nucleus preserved by layers of ice and dust. The fact that it remains intact as it approaches the sun is remarkable. Many comets disintegrate under the stress of solar heating. Yet 3I Atlas's CO₂-driven activity, observed as it sublimates at distances where water ice would remain frozen, suggests that its outgassing mechanisms are uniquely suited to its environment. This adaptation may have allowed it to persist for billions of years, a silent voyager through the void. The implications of 3I Atlas's age extend beyond its own history. If the comet is indeed older than the solar system, it carries chemical signatures from a time when the galaxy was younger and richer in heavy elements. The presence of carbon dioxide, cyanide, and nickel in its coma offers a window into the primordial building blocks of planetary systems. These elements, forged in the hearts of ancient stars and scattered by supernovae, are essential to the formation of planets and the emergence of life. By studying 3I Atlas, we may uncover the universal recipe for habitable worlds, a recipe written in the ice and dust of interstellar comets. As 3I Atlas nears perihelion on 29 October 2025, its fate hangs in the balance. The sun's heat will accelerate its activity, driving off volatile ices and shaping its coma into a luminous ethereal tail. Yet this transformation is not its end. After its closest approach, the comet will retreat into the darkness of interstellar space, carrying with it the memories of its distant past. Its journey, though fleeting in human terms, is part of a grander cycle: the ejection, travel, and eventual reabsorption of interstellar objects into the cosmic web. In this endless exchange, the boundaries between stars dissolve, and the universe reveals itself as a single interconnected entity. As 3I Atlas hurtles toward perihelion, its coma, a glowing envelope of gas and dust, expands like a breath exhaled into the cold vacuum of space. This tenuous cloud, invisible to the naked eye but captured in exquisite detail by the Hubble and James Webb Space Telescopes, is a laboratory of cosmic chemistry. Here, the sublimation of ices and the ejection of volatiles create a dynamic environment where molecules collide, react, and evolve. The coma is not merely a veil around the nucleus. It is a record of the comet's past and a harbinger of its future. The coma's composition is a mosaic of complexity. Carbon dioxide dominates, its abundance suggesting a formation temperature colder than any in the solar system. Water vapor and carbon monoxide, though present in smaller quantities, add nuance to the comet's story. Traces of cyanide and nickel, detected by ground-based telescopes, hint at the presence of organic compounds and metallic elements, essential ingredients for life. These substances, forged in the crucibles of dying stars and distributed by stellar winds, are now part of a drifting, icy nucleus that has traveled billions of kilometers across the galaxy. The coma's evolution is equally fascinating. As 3I Atlas draws closer to the sun, its activity intensifies. Small dust particles, ejected at speeds of 22 meters per second, form a faint anti-solar tail that stretches millions of kilometers into space. Larger grains, moving more slowly, linger near the nucleus, creating a diffuse reddish glow. This color, caused by irradiated organic compounds, is reminiscent of the D-type asteroids and the interstellar comet 2I Borisov, linking 3I Atlas to a broader family of celestial objects. The coma's asymmetry, its elongation toward the sun, and the growth of its tail, reflects the interplay between solar radiation pressure and the comet's internal dynamics. Yet the coma is not static. Observations from the Vera C. Rubin Observatory and the Transiting Exoplanet Survey satellite TESS reveal that 3I Atlas has been active for months, even when it was 6.4 AU from the Sun. This early activity, driven by the sublimation of carbon dioxide and carbon monoxide, suggests that the comet's nucleus is a patchwork of ices, each with its own melting point. The gradual brightening of the coma as the comet approaches perihelion is a testament to the Sun's inexorable influence, a force that will ultimately dictate the comet's fate. By studying the coma, we gain not only insights into 3I Atlas's chemistry, but also a deeper appreciation for its role in the cosmic ecosystem. The materials it carries, ices, organics, metals, are the seeds of planets and the precursors to life. As 3I Atlas continues its journey, it reminds us that the universe is a recycling ground, where the remnants of one star system become the building blocks of another. In its fragile, glowing coma, we see the echoes of a distant past and the promise of a future yet to unfold. In the vast tapestry of the universe, where stars burn like distant lanterns and galaxies spiral in silent dances, the comet 3I Atlas drifts a solitary traveler from the depths of interstellar space. Its coma, a tenuous cloud of gas and dust, glows with a reddish hue, a spectral signature that whispers of ancient histories and alien chemistries. What secrets does this ethereal shroud conceal? Why does 3I Atlas differ so profoundly from the comets of our own solar system? As we peer into the heart of its coma, we find not just ice and dust, but a mosaic of molecules that defy familiar patterns. Carbon dioxide, water ice, cyanide, and nickel vapor swirl in a delicate balance, their proportions hinting at a birthplace far removed from the Sun's embrace. This is no ordinary comet. It is a relic of another stellar nursery, a time capsule forged in the crucible of a distant star's youth. To decode its chemistry is to unravel the story of its origins, and perhaps glimpse the cosmic forces that shaped its journey across the void. The coma of 3I Atlas is born from the Sun's relentless touch. As the comet ventures closer to our star, solar radiation penetrates its icy nucleus, triggering a process known as sublimation, the direct transformation of solid ice into gas. This metamorphosis releases volatile compounds trapped beneath layers of frozen rock and dust, creating a luminous envelope that expands outward. Yet the composition of this envelope tells a tale unlike any other. Unlike the comets of our solar system, which often exhibit a dominant presence of water ice, 3I Atlas's coma is dominated by carbon dioxide, CO₂, with a mixing ratio of CO₂ to water of approximately 8:1. This staggering imbalance suggests a formation far from its parent star, beyond the CO₂ frost line, where temperatures are so frigid that even this molecule condenses into solid form. What gives 3I Atlas its characteristic red hue? The answer lies in the irradiated organic compounds that permeate its coma. These complex molecules, forged in the shadowed recesses of interstellar space, absorb blue light and reflect the longer wavelengths of red. Spectroscopic analysis from the James Webb Space Telescope, JWST, and ground-based observatories reveal the presence of fine-grained water ice, carbon monoxide, CO, and carbonyl sulfide, OCS, alongside fleeting traces of water vapor. The interplay of these substances creates a coma that is both vibrant and enigmatic, a testament to the comet's exposure to cosmic radiation and the turbulent history of its parent star's protoplanetary disk. Yet the most striking feature of 3I Atlas's chemistry is its scarcity of carbon chain compounds. Molecules like dicarbon, C2, and tricarbon, bond C3, which are abundant in many solar system comets. Observations by the MDM Observatory and others have found no significant traces of these species, suggesting a stark depletion in long-chain hydrocarbons. Instead, the comet emits cyanide, CN, gas and atomic nickels, nickel, Ni, vapor at concentrations akin to those observed in 2I Borisov. The absence of iron vapor, however, introduces a puzzle. Why does nickel persist while its metallic cousin vanishes? Could this be a quirk of the comet's internal chemistry, or a clue to its violent past? The chemical fingerprint of 3I Atlas is a key to unlocking its origins. Its CO₂-rich coma implies that it formed in a region of its parent system where volatile ices could freeze, a realm analogous to the Kuiper belt in our own solar system. Yet the scarcity of water ice in the nucleus and the dominance of CO₂ suggest a different evolutionary path. One hypothesis posits that 3I Atlas's nucleus is encased in a thick, insulating crust of water ice, shielding its CO₂-rich interior from rapid sublimation. Alternatively, the comet may have inherited its CO₂ abundance from a protoplanetary disk rich in this molecule, shaped by the intense radiation of its parent star. Either scenario paints a picture of a system distinct from our own, one where the balance of volatiles diverges from the norms of the solar system's icy bodies. The detection of cyanide and nickel vapor adds another layer to this mystery. Cyanide, a molecule central to the chemistry of life, is often associated with the organic complexity of comets. Its presence in 3I Atlas hints at a reservoir of prebiotic chemistry, perhaps preserved for billions of years in the deep freeze of interstellar space. Nickel, on the other hand, is a refractory element typically found in the cores of planetary bodies. Its release into the coma may stem from the thermal decomposition of nickel-containing organic compounds, such as nickel tetracarbonyl, under the influence of solar radiation. Yet the absence of iron, a metal often paired with nickel in cometary outgassing, raises questions about the comet's internal structure. Is 3I Atlas a remnant of a shattered planetary body, or does its chemistry reflect the unique conditions of its birthplace? Even more intriguing is the comet's apparent lack of carbon chain compounds. In the solar system, these molecules are ubiquitous in cometary Comae, their presence a hallmark of the complex organic chemistry that flourished in the protosolar nebula. The absence of C2 and C3 in 3I Atlas suggests a paucity of long-chain hydrocarbons, possibly due to the harsh radiation environment of its parent star's disk. Or perhaps the comet's journey through interstellar space stripped it of these fragile molecules, leaving behind only the hardiest survivors. Whatever the case, 3I Atlas stands as a stark contrast to the comets of our own backyard, a reminder that the building blocks of planets and life may take countless forms across the cosmos. To understand 3I Atlas fully, we must look beyond its chemistry and into the mechanics of its motion. How did this interstellar wanderer arrive at our doorstep? What trajectory carried it through the void? And what forces shaped its path? The answers lie not only in the comet's current behavior, but in the intricate dance of its rotation and surface activity. As 3I Atlas spins, its irregular nucleus casts shadows and reveals variations in brightness, offering clues to its structure and history. Yet the coma's obscuring veil complicates these observations, blurring the lines between the comet's intrinsic properties and the transient effects of solar heating. By untangling these threads, we may uncover the secrets of its spin cycle, and in turn, the gravitational tides that propelled it across the galaxy. The coming chapters will delve into the comet's rotational dynamics, tracing the rhythms of its dance through the solar system. Here, the interplay of light and shadow will illuminate not just the comet's shape, but the forces that govern its fate. As we follow 3I Atlas's journey, we are reminded that every twist of its tail, every flicker of its coma, is a message from the stars, a message waiting to be deciphered. In the vast, silent expanse of the cosmos, every object tells a story through its motion. Comets, those ancient wanderers of the interstellar void, are no exception. Among them, 3I Atlas, a transient visitor from the depths of the galaxy, spins through the solar system with a rhythm as enigmatic as its origins. Rotation, a fundamental property of celestial bodies, shapes the life of a comet in ways both subtle and profound. For 3I Atlas, its spin influences how it interacts with sunlight, how it sheds gas and dust, and even how its fragile nucleus might respond to the gravitational tugs and thermal stresses of its passage near the sun. Yet, measuring this rotation is a challenge akin to deciphering the heartbeat of a distant star cloaked in shadow. The comet's nucleus, shrouded in a veil of reflective dust and gas, obscures direct observation, forcing astronomers to rely on indirect clues, fluctuations in brightness, the shifting contours of its coma, and the spectral signatures of its outgassing. To understand 3I Atlas's spin is to peer into the mechanics of its survival, a dance of balance and instability as it hurtles through the inner solar system. The rotation of a comet is not merely a curiosity, it is a critical factor in its evolution. Most comets, including 3I Atlas, are irregularly shaped, their nuclei often resembling lumpy potatoes or fractured rubble piles. This asymmetry leads to periodic changes in brightness as the comet turns, much like a spinning top, whose uneven surface casts varying shadows. For 3I Atlas, early photometric observations conducted in July 2025 hinted at a rotation period of approximately 16.79 hours, derived from subtle variations in its light curve. However, the comet's Coma, a dynamic cloud of gas and dust, complicates these measurements. The Coma reflects sunlight in unpredictable ways, masking the true brightness variations of the nucleus. Astronomers liken this challenge to trying to discern the ticking of a clock submerged in fog to refine their understanding. Researchers turn to high-resolution imaging from the Gran Telescopio Canarias and the Hubble Space Telescope. These instruments captured the comet's Coma in exquisite detail, revealing not just its overall structure, but also the subtle asymmetries in its shape. By analyzing the evolution of these features over time, scientists inferred that 3I Atlas's nucleus might rotate with a period closer to 16.16 hours. Yet, even this estimate carries uncertainties. The comet's activity, its release of gas and dust, continuously reshapes its Coma, altering the light it emits and complicating efforts to isolate the nucleus's intrinsic rotation. Additionally, the orientation of the comet's rotational axis remains a mystery. Does it spin like a top with its axis nearly perpendicular to its orbital plane? Or does it tumble like a wobbling gyroscope? Clues lie in the distribution of its outgassing jets and the alignment of its Coma's elongation, which could hint at the direction of its spin. Theoretical models further complicate the picture. For instance, if 3I Atlas's rotation is driven by torques from asymmetric outgassing, gas escaping unevenly from its surface, it might experience gradual changes in its spin rate or even chaotic tumbling. Such behavior has been observed in other comets such as 67P Churyumov-Gerasimenko, where the Philae lander documented a nucleus rotating in a complex, non-principal axis motion. For 3I Atlas, the question is not just how it spins, but why. Is its rotation a relic of its formation in another star system, or has it been altered by gravitational interactions during its journey through interstellar space? The answers lie buried in the data, waiting to be unearthed by meticulous analysis. Understanding 3I Atlas's rotation is not merely an academic exercise. It holds the key to predicting the comet's fate. Ampera's rapidly spinning nucleus, particularly one with an irregular shape, is vulnerable to centrifugal forces that could destabilize it. If the comet's rotation period is indeed around 16 hours, its angular momentum is moderate, suggesting a balance between cohesion and instability. However, even a modest spin rate could lead to catastrophic outcomes under certain conditions. For example, if the nucleus contains loosely bound material or fractures from past collisions, the stress of rotation might trigger a breakup. Such events are not unheard of in the solar system. In 2019, the interstellar comet 2I Borisov exhibited signs of potential disintegration as it neared the Sun. The alignment of 3I Atlas's rotation axis also plays a crucial role in its interaction with the Sun. If the nucleus is oriented such that its poles face the Sun, the heating of its surface will be uneven, creating localized hotspots that drive asymmetric outgassing. This in turn could produce jets of gas and dust that alter the comet's trajectory or even influence its spin direction. Conversely, if the equator is aligned with the Sun, the heating will be more uniform, leading to a steadier release of material. The absence of a prominent tail during 3I Atlas's perihelion passage, despite its high activity, might be linked to its spin orientation. If the comet's rotation is such that its outgassing is distributed evenly around its nucleus, the resulting dust and gas might not coalesce into a single visible tail, but instead spread diffusely, blending with the Coma. Moreover, the rotation of 3I Atlas provides insights into its internal structure. AMPER's rigid, monolithic nucleus would maintain a stable rotation, while a fragmented or porous interior might exhibit more erratic behavior. The fact that the comet's brightness variations have decreased over time, from a 0.3 magnitude swing in early July to a 0.2 magnitude shift by late July, suggests that the nucleus is becoming increasingly obscured by its coma. This could indicate a growing layer of dust insulating the nucleus, dampening its brightness fluctuations and possibly slowing its rotation. Alternatively, the decrease might reflect changes in the comet's activity, such as a shift in the location or intensity of its outgassing jets. Either way, the interplay between rotation and activity reveals the dynamic, ever-changing nature of 3I Atlas. Comparisons to other comets further illuminate the significance of rotation. For instance, the solar system's Jupiter family comets, which originate from the Kuiper belt, often exhibit rapid rotations due to their frequent gravitational encounters with the gas giant. By contrast, long-period comets from the Oort cloud tend to have slower, more chaotic spins. 3I Atlas, an interstellar interloper, defies easy categorization. Its rotation period places it somewhere between these extremes, hinting at a formation history shaped by the unique dynamics of its parent star system. If its spin is indeed a remnant of its birthplace, it offers a rare glimpse into the processes that govern planetary systems beyond our own. As 3I Atlas continues its journey through the inner solar system, its rotation sets the stage for the next chapter of its story, the eruption of gas and dust. The sun's relentless pull accelerates the comet's approach, heating its nucleus to the point where volatile ices sublimate in a frenzy of activity. Yet the timing, intensity, and composition of these eruptions depend not only on the sun's energy, but also on the comet's internal structure and spin state. AMPER's rapidly rotating nucleus might generate asymmetrical jets, while a slower, more stable rotation could produce a uniform outflow of material. The question now shifts from how 3I Atlas spins to what ignites its transformation as it plunges toward perihelion. What unseen forces lie beneath its icy shell, ready to awaken? And how will the interplay of rotation, activity, and solar radiation shape the final act of this interstellar traveler? The answers await in the coming months, as 3I Atlas dances ever closer to the heart of the solar system. The universe is a theater of transformation, where even the coldest, most ancient relics are reshaped by the inexorable pull of energy and time. 3I Atlas, a wanderer from the depths of interstellar space, now finds itself in the gravitational embrace of the sun. Its journey, a cosmic ballet choreographed by gravity and entropy, has brought it to a critical juncture, the moment when its frozen heart begins to breathe, as the comet's nucleus, a relic of a distant stellar nursery, absorbs the sun's radiant heat. Its surface undergoes a metamorphosis. Frozen carbon dioxide, water, and other volatile ices sublimate into gas, transforming the comet into a glowing ethereal spectre. This process, both violent and delicate, is not merely a spectacle of light and shadow, but a window into the chemistry of another world, the physics of interstellar travel, and the enduring resilience of matter against the void. Why does 3I Atlas breathe as it nears the sun? The answer lies in the dance between ice and fire, a phenomenon that has shaped comets for billions of years, and one that offers clues to the origins of life itself. At the heart of 3I Atlas's transformation is sublimation, the direct transition of a solid into gas without passing through a liquid phase. The sun, a searing sphere of nuclear fusion, radiates energy across the solar system, warming the comet's nucleus as it spirals inward. The temperature of the nucleus rises incrementally, but the effects are dramatic. Carbon dioxide, which dominates the comet's volatile inventory, sublimates first. Unlike water ice, which requires higher temperatures to vaporize, CO2 turns to gas at a mere nearer 57 degrees Celsius, a threshold easily reached at 3.32 AU from the Sun, the distance where the James Webb Space Telescope first observed 3I Atlas in August 2025. This sublimation creates a coma, a vast diffuse cloud of gas and dust that surrounds the nucleus. The coma of 3I Atlas is not uniform. It is a dynamic tapestry of particles and molecules, with CO2 gas forming a sprawling envelope that stretches 348,000 kilometers, 2116,000 miles in radius. This is equivalent to nearly a quarter of the distance between the Earth and the Moon, a staggering scale that underscores the comet's potency as an outgassing machine. The process is not silent. As volatile ices sublimate, they release trapped dust grains, which are carried outward by the expanding gas. These grains vary in size, from microscopic specks to millimeter-sized fragments, and their behavior is dictated by physics. Smaller particles, accelerated by solar radiation pressure, form a faint anti-solar tail that points directly away from the sun. Larger grains, less affected by radiation, drift more slowly, creating a broader, dust-rich tail that lags behind the nucleus. Meanwhile, the sun-facing side of the comet experiences a unique phenomenon, a sunward-pointing plume of dust and gas. This plume, observed in July and August 2025, is a direct consequence of the nucleus's asymmetry and the localized heating of its surface. Just as a candle flame tilts toward the heat source, the comet's outgassing is concentrated on the hemisphere facing the sun, producing a luminous, elongated feature that defies the intuitive expectation of a tail. The interplay between CO2 and water ice further complicates the comet's activity. While CO2 dominates at distances beyond 3 AU, water ice becomes increasingly significant as the comet approaches the sun. By the time 3I Atlas reaches perihelion in October 2025, its proximity to the sun will have raised surface temperatures sufficiently to trigger widespread water sublimation. This dual-phase outgassing creates a layered coma, with CO2-rich regions closer to the nucleus and water vapor dominating the outer edges. The detection of water ice and vapor by the Swift Observatory and the James Webb Space Telescope in late July and August 2025 confirms this dynamic. Moreover, the presence of fine submicron water ice grains, likely amorphous in structure, suggests that the comet's activity is not confined to its nucleus but extends into the coma itself, where ice particles continue to sublimate en route to the vacuum of space. The sublimation of 3I Atlas's volatile ices is more than a mechanical process. It is a testament to the comet's survival. The fact that its nucleus remains intact despite the intense solar heating speaks volumes about its internal structure and composition. The absence of observed outbursts, sudden, explosive releases of gas and dust, indicates that the comet is not experiencing catastrophic destabilization. Instead, its activity appears to follow a steady, predictable pattern, akin to the gentle exhalation of a sleeping giant. This stability is remarkable, considering the extreme conditions the comet faces. At 58 kilometers per second, 38 kilometers per second, 36 ms, 3I Atlas is the fastest interstellar object ever observed, a velocity that suggests it hails from a system where gravitational interactions were fierce enough to eject it into the galactic abyss. Yet here it is, a fragile yet resilient traveler, its nucleus shielded by a layer of insulating material that may protect deeper reservoirs of water ice from immediate sublimation. However, this equilibrium is precarious. As the comet approaches perihelion, the sun's influence will intensify, and the balance between sublimation and structural integrity may falter. Previous interstellar visitors, such as 2I Borisov, have demonstrated that comets can fragment under the strain of solar heating. In 2019, Borisov's nucleus split apart, leaving behind a trail of debris that offered astronomers a fleeting glimpse into the chaotic interior of an alien world. Could 3I Atlas suffer a similar fate? The answer lies in the unseen forces at play within its nucleus. If its crust is thin or fractured, the rapid expansion of sublimating gases could generate internal pressures sufficient to rupture the comet. Conversely, if the nucleus is encased in a thick insulating mantle, perhaps a product of centuries of exposure to interstellar radiation or collisions with other objects, it may endure the sun's fury unscathed. Either scenario would provide invaluable insights into the nature of interstellar comets and the environments from which they originate. Beyond its physical transformations, 3I Atlas's activity holds profound implications for astrochemistry. The detection of carbon monoxide, carbonyl sulfide, cyanide, and atomic nickel in its coma paints a picture of a chemically diverse and potentially primordial object. These molecules, forged in the cold crucibles of interstellar space or the protoplanetary disks of distant stars, carry the fingerprints of their birthplace. The presence of heavy isotopes of carbon in CO₂, for instance, may reveal the conditions under which the comet formed, whether in a region of the galaxy where supernova explosions enrich the surrounding medium with heavier elements, or in a quieter, more isolated corner of a molecular cloud. Similarly, the scarcity of carbon chain compounds like C2 and C3, which are common in solar system comets, suggests that 3I Atlas's parent star system may have had a different chemical history. These findings challenge the assumption that all comets, regardless of origin, share a universal composition. Instead, they hint at a cosmos where the building blocks of life or its precursors are distributed unevenly, shaped by the unique histories of individual star systems. Even the absence of certain compounds carries meaning. The lack of iron vapor in 3I Atlas's coma, despite the detection of nickel, is puzzling. In solar system comets, nickel and iron are typically found in roughly equal proportions, both released through the breakdown of complex organic molecules. The discrepancy in 3I Atlas raises questions about the chemical pathways that govern its outgassing. Is its nucleus deficient in iron-bearing compounds, or do other processes such as differential sputtering or photodissociation suppress the release of iron? Answering these questions requires a deeper understanding of the comet's surface chemistry, a task complicated by the difficulty of distinguishing between the nucleus and coma in observational data. Yet this ambiguity is itself a clue, a reminder that the universe is replete with mysteries waiting to be unraveled. As 3I Atlas continues its solar pilgrimage, the sublimation of its volatile ices tells a story not only of transformation, but of endurance. Its ability to withstand the sun's relentless heat speaks to the durability of its structure, the ingenuity of its chemistry, and the resilience of matter itself. Yet this resilience is not eternal. The comet's fate, whether it disintegrates into stardust or escapes into the galactic dark, is tied to forces beyond its control. But before we speculate on its demise, we must consider the deeper question: how old is this traveler? How long has it wandered the cosmos, bearing witness to the rise and fall of stars, the birth of planets, and the quiet hum of time? The answers lie not in the present, but in the past, a past etched into the comet's trajectory, its composition, and the faint echoes of its origin. To understand 3I Atlas fully, we must peer beyond its glowing coma and into the vast uncharted expanse from which it came. Imagine a solitary traveler adrift in the vastness of space, older than Earth itself. Such is the case with 3I Atlas, a comet whose origins stretch back to the dawn of the Milky Way. Unlike the fleeting visitors of our solar system, this interstellar wanderer carries the secrets of an ancient epoch, a relic from a time when the galaxy was still forming. Its journey through interstellar space, spanning billions of years, raises profound questions. How long has it roamed the cosmos? What forces shaped its path? And what can its existence reveal about the universe's earliest days? As we trace the comet's trajectory and analyze its motion through the galactic disk, we uncover a story etched in the fabric of cosmic time, a tale of endurance, transformation, and the enduring mystery of our place in the universe. The key to unraveling 3I Atlas's age lies in its velocity and position within the Milky Way. By breaking down its hyperbolic excess velocity into components, radial, transverse volts, and vertical watts, astronomers have determined that the comet's motion aligns with the dynamics of the galaxy's thick disk population. This population, composed of older stars with lower metallicity, fewer heavy elements than the Sun, dates back to the Milky Way's formation phase, roughly 10 to 12 billion years ago. The vertical component of 3I Atlas's velocity, watts, mean under 118.5 kilometers per second, relative to the Sun, suggests it follows a tilted orbit, characteristic of thick disk objects, which move in chaotic paths above and below the galactic plane. Matthew Hopkins and his team calculated that 3I Atlas likely originated in the thick disk, placing its age between 7.6 and 14 billion years. This estimate hinges on the typical lifetimes of thick disk stars, which are among the oldest in the galaxy. Independent analyses by Asta Taylor and Daryl Seligman corroborate this, narrowing the comet's age to 311 billion years. Either way, 3I Atlas predates the solar system by billions of years, making it the oldest known interstellar object to grace our cosmic neighborhood. Such an age is staggering, considering that the Sun itself is a mere 4.6 billion years old. To put this into perspective, while the solar system formed in the bustling heart of a spiral arm, 3I Atlas emerged in a quieter, denser region of the galaxy, where stars were still coalescing into their present-day configurations. The comet's trajectory also provides clues about its journey. Its arrival in the solar system came from the direction of the galactic center, a region teeming with stars and nebulae. However, its high vertical velocity indicates it has spent much of its existence oscillating above and below the galactic plane, avoiding the dense star fields that might have stripped it of volatile ices. This dynamic history explains why 3I Atlas remains intact despite its ancient age. Unlike comets in the Oort cloud, which are periodically nudged into the inner solar system by passing stars or galactic tides, 3I Atlas's interstellar origin means it never belonged to a planetary system. Instead, it has wandered freely for eons, propelled by the gravitational interactions of stars and molecular clouds. Its path a testament to the galaxy's turbulent past. The discovery of a 7-billion-year-old comet challenges our understanding of cometary longevity and the evolution of the Milky Way. Traditionally, comets are considered transient bodies, their volatile ices eroded by solar radiation and collisions over millions of years. Yet 3I Atlas has endured for epochs, suggesting its nucleus possesses an extraordinary resilience. One possibility is that its icy composition is shielded by a thick insulating crust, preserving volatile ices beneath. Observations by the James Webb Space Telescope, JWST, support this hypothesis, revealing a coma rich in carbon dioxide and water, with sublimation patterns indicating a nucleus that may have remained frozen until its recent approach to the Sun. Moreover, 3I Atlas's ancient age offers a unique window into the conditions of the early universe. The comet's low metallicity, implied by its thick disk origin, suggests it formed in a stellar nursery with limited heavy elements, a stark contrast to the chemically enriched environments of modern star-forming regions. This composition mirrors the primordial material that seeded the first generations of stars, providing a direct link to the Milky Way's infancy. By studying the isotopic ratios of gases like carbon dioxide and the distribution of organic compounds in its coma, scientists can reconstruct the chemical processes that shaped the galaxy billions of years ago. For instance, the presence of carbon-13 enriched CO₂ in 3I Atlas's coma hints at exposure to intense cosmic rays or proximity to a supernova remnant in its youth. Such findings could refine models of stellar nucleosynthesis and the dispersal of heavy elements across the cosmos. Perhaps most intriguing is the comet's role as a time capsule. Its survival implies that interstellar objects can retain their primordial characteristics for billions of years, offering a pristine record of the materials that existed before the solar system formed. This has profound implications for astrobiology, as organic molecules like cyanide and carbonyl sulfide, detected in 3I Atlas's coma, are precursors to complex chemistry. Could such comets have delivered the building blocks of life to nascent planetary systems? While the solar system's own comets provide clues, 3I Atlas represents an external source, its composition unaltered by the gravitational and thermal history of any planetary system. Future studies of its isotopic composition and mineralogy could shed light on the universality of prebiotic chemistry in the cosmos. Yet the comet's age also raises existential questions. If 3I Atlas has roamed the galaxy for 7 billion years, it has witnessed the rise and fall of countless stars, the formation of spiral arms, and the mergers of dwarf galaxies. Its journey is a microcosm of the Milky Way's evolution, a silent observer of cosmic cycles. In this sense, 3I Atlas is not merely an object of scientific curiosity, but a symbol of the universe's enduring interconnectedness. Every atom in its nucleus, forged in the crucibles of ancient stars, connects it to the web of matter that binds galaxies together. Its passage through the solar system is a fleeting encounter, a reminder that even the smallest travelers carry the weight of cosmic history. But how did 3I Atlas acquire its trajectory? Why does it now hurtle through the solar system at such a blistering pace? The answers lie in the violent dance of planetary formation, a process that has scattered countless objects into interstellar exile. To understand the comet's origin, we must look inward to the chaotic birth of its parent star system. Just as the solar system's outer planets sculpted the Kuiper belt and Oort cloud, gravitational interactions in 3I Atlas's home system likely flung it into the void. This leads us to the next chapter in the comet's saga, the cataclysmic events that severed it from its stellar cradle and set it on its millennia-long journey. By tracing the comet's past, we gain insight not only into its own history, but into the universal mechanisms that shape the destinies of stars, planets, and the wandering relics that drift between them. In the vast, silent expanse of the cosmos, comets are born as fragile relics of planetary formation, icy wanderers sculpted in the frigid outskirts of star systems. Yet how do these frozen bodies escape their cradles and drift into the void? The story of 3I Atlas begins not in the present, but in a distant, chaotic past, when gravitational forces acted as cosmic slingshots. Imagine a scene where a young star's planetary nursery teems with activity, planets forming, colliding, and scattering debris. Amidst this turmoil, a comet like 3I Atlas might have been hurled from its home by the sheer gravitational might of a giant planet or the disruptive pull of a passing star. Such ejections are not mere accidents. They are the inevitable consequences of stellar youth. Today, as 3I Atlas hurtles through the inner solar system at 58 kilometers per second, a speed far exceeding that of the sun's gravitational embrace, it carries with it the echoes of this violent expulsion. Its trajectory, a hyperbolic arc stretching beyond the boundaries of our cosmic neighborhood, whispers of a journey that began eons ago. To unravel the origins of 3I Atlas is to peer into the mechanics of cosmic exile, a process as ancient as the stars themselves. The ejection of interstellar objects like 3I Atlas is a testament to the dynamic violence of young star systems. In the early stages of a star's life, its protoplanetary disk is a chaotic arena. Gas giants born from the accretion of swirling material migrate inward, destabilizing the orbits of smaller bodies. These migrations trigger gravitational scattering, where icy comets are flung into the void. Ampere's single close encounter with a massive planet, say a Saturn or Jupiter-sized world, can impart enough kinetic energy to eject a comet from its system entirely. Alternatively, the gravitational tug of a passing star, perhaps a neighbor in a crowded stellar nursery, can disrupt the delicate balance of orbits, sending a comet spiraling into interstellar space. For 3I Atlas, the evidence of such a violent history lies in its velocity. Its hyperbolic excess speed of 58 kilometers per second is unparalleled among known interstellar objects, dwarfing the 26 kilometers per second of 1I Oumuamua and 32 kilometers per second of 2I Borisov. This speed suggests an ejection from a system with particularly energetic dynamics. One plausible scenario involves a binary star system, where two stars orbit each other. In such environments, gravitational interactions are amplified, making ejections more frequent. Ampere's comet caught in the gravitational dance of twin stars might be flung outward with greater force, explaining 3I Atlas's extreme velocity. Another possibility is a collision between two planetary embryos, a cataclysmic event that could scatter debris into interstellar space. Moreover, 3I Atlas's composition offers clues to its origin. Its coma is unusually rich in carbon dioxide, a volatile compound that condenses only in the coldest reaches of a star system. This implies that 3I Atlas formed far from its parent star, beyond the CO2 frost line, where temperatures are low enough for such molecules to freeze. Such a location aligns with the idea of a distant icy reservoir, a Kuiper belt analog in another system that was destabilized by gravitational perturbations. The high CO2 content also contrasts with the water-dominated comas of solar system comets, hinting at differences in the chemistry of its parent system. Whether expelled by a planet or a star, 3I Atlas's journey is a relic of the turbulent birth of its homeworld, a frozen messenger carrying the secrets of its origins. The ejection of 3I Atlas is not an isolated event, but a window into the broader processes shaping the galaxy. Simulations suggest that every young star system produces thousands of such interstellar exiles, their trajectories scattered like stardust across the Milky Way. These objects, though individually rare, collectively form a vast, unseen population drifting between the stars. Their existence challenges the notion of isolation in the cosmos, revealing a web of gravitational interactions that bind star systems together. When 3I Atlas passes through the solar system, it is not merely a visitor, but a thread in this cosmic tapestry, a fragment of another system's history now interwoven with ours. The implications extend beyond astronomy. The study of interstellar objects, like 3I Atlas, could revolutionize our understanding of planetary formation. By analyzing their compositions, we gain insights into the conditions of alien protoplanetary disks. For instance, 3I Atlas's CO₂-rich Coma suggests that its parent system may have experienced different evolutionary paths than our own, perhaps forming in a region of the galaxy with distinct chemical abundances. Such comparisons could help identify universal patterns in planet formation or highlight the diversity of stellar nurseries. Additionally, the discovery of 3I Atlas underscores the importance of monitoring the skies for transient phenomena. With projects like the Vera C. Rubin Observatory coming online, the detection of interstellar objects will become routine, offering a treasure trove of data on the galactic scale dynamics of ejections. Yet the story of 3I Atlas also raises profound questions about the nature of cosmic exile. Why does a comet endure billions of years of solitude, untouched by the warmth of a star? What secrets lie in its nucleus preserved in the deep freeze of interstellar space? These questions are not purely scientific but philosophical, touching on themes of resilience, transformation, and the passage of time. As 3I Atlas approaches perihelion, its nucleus warms and its frozen heart begins to breathe. For a brief moment, it becomes a beacon of its ancient past, a fleeting glimpse into the chaos of stellar youth. While the science of 3I Atlas's ejection is grounded in physics and observation, its journey transcends the realm of data. It invites us to consider our place in the cosmos, not as isolated observers, but as participants in a grand, interconnected story. The same gravitational forces that expelled 3I Atlas from its home may have shaped the solar system itself, sculpting the orbits of planets and moons. In this sense, the comet is not merely an interstellar traveler, but a mirror reflecting the universal processes that govern all star systems. As 3I Atlas continues its path, it carries with it the potential to answer questions we have yet to ask. What else lies hidden in the depths of interstellar space? What other fragments of cosmic history await discovery? And if we could trace its origins to a long-lost star system, what might we learn about the possibilities of life elsewhere? These are not idle musings, but the driving questions of human exploration, a quest to understand not only the universe but our place within it. The story of 3I Atlas is but one chapter in this epic tale, a reminder that even the smallest, coldest wanderer holds the power to illuminate the vast, uncharted expanse of the cosmos. This narrative structure balances scientific rigor with poetic reflection, ensuring that each segment of the script builds upon the last while leaving room for contemplation. The transition sets the stage for deeper exploration of themes like cosmic interconnectedness, the search for extraterrestrial life, or the philosophical implications of interstellar travel. In the vast, silent expanse of the cosmos, where stars burn like distant embers, galaxies spiral in endless dance, a new traveler emerged. Discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, Atlas, at Rio Hurtado, Chile. 3I Atlas, a comet born not in our solar system, but among the stars of another, has ignited a wave of curiosity and awe. Its arrival marks a profound moment in astronomical history, for it is the third interstellar object ever confirmed to traverse our cosmic neighborhood, like a messenger from the depths of interstellar space. 3I Atlas carries with it secrets of its origin, its journey, and the conditions of the stellar nursery from which it sprang. This comet is no ordinary wanderer. It hurtles through the solar system at a blistering speed of 58 kilometers per second, its trajectory a hyperbolic arc that ensures it will never return. Unlike the planets and asteroids that orbit the Sun in predictable cycles, 3I Atlas is a transient visitor, a fleeting glimpse into the wider galactic tapestry. Its discovery echoes the first interstellar object, 1I Oumuamua, and the enigmatic 2I Borisov, but it is distinct in its own right. From its chemical composition to its origins in the Milky Way's ancient thick disk, 3I Atlas offers a rare opportunity to study the building blocks of worlds beyond our own. As we trace its path through the heavens, we are reminded of our small place in the universe. 3I Atlas is not merely a scientific curiosity. It is a symbol of the infinite connections between stars and the shared heritage of planetary systems. To observe this comet is to witness the echoes of stellar births and deaths, the remnants of protoplanetary disks scattered across the cosmos. In its icy nucleus and glowing coma, we see reflections of our own solar system's infancy, glimpses of the processes that forge the planets and the life they nurture. Yet, for all its strangeness, 3I Atlas feels strangely familiar. Its red-hued coma, rich in carbon dioxide and organic compounds, mirrors the ingredients of solar system comets. Its dust trails and gas emissions speak of the same forces that sculpted the Kuiper Belt and Oort cloud. In studying this interstellar traveler, we are not only unraveling the mysteries of its origin, but also deepening our understanding of the universality of planetary formation. 3I Atlas is a bridge between the known and the unknown, a testament to the boundless creativity of the cosmos. And as we prepare to witness its closest approach to the Sun in October 2025, we stand on the threshold of discovery, poised to learn more about the nature of our universe and our place within it. To comprehend the significance of 3I Atlas, we must first understand the forces that govern its motion. Unlike the planets, which are bound to the Sun in elliptical orbits, 3I Atlas follows a hyperbolic trajectory, a path that curves sharply under the influence of the Sun's gravity, but ultimately escapes its pull. This trajectory is defined by the comet's hyperbolic excess velocity, the speed it possesses relative to the Sun that exceeds the gravitational binding energy. For 3I Atlas, this velocity is an astonishing 58 kilometers per second, nearly double that of 2I Borisov, and more than twice that of 1I Oumuamua. Such a speed is not merely a product of chance. It is a signature of the comet's interstellar origin. Only an object that has traveled vast distances through the galaxy, unbound by any star's gravitational embrace, could arrive with such kinetic energy. The Sun, however, does not leave this visitor unaffected. As 3I Atlas ventures closer to our star, the intense heat triggers a transformation. The comet's nucleus, a frozen core of rock, ice and organic material, begins to warm. Volatile ices, primarily carbon dioxide, water and carbon monoxide, sublimate, turning directly from solid to gas in a process that drives away dust and gas in a luminous coma. This coma, a tenuous cloud surrounding the nucleus, expands outward, forming a tail that stretches millions of kilometers. The dynamics of this activity are governed by the balance between solar heating and the comet's internal structure. Observations by the Hubble Space Telescope and the James Webb Space Telescope have revealed that 3I Atlas's coma is unusually rich in carbon dioxide, a finding that raises intriguing questions about its formation environment. The size of 3I Atlas's nucleus remains a subject of debate. Estimates from Hubble data suggest it ranges between 0.32 and 5.6 kilometers in diameter, though the most probable figure is less than 1 kilometer. This uncertainty stems from the difficulty of distinguishing the nucleus's faint glow from the much brighter coma. Yet, even a small nucleus can yield profound insights. The rate at which dust and gas are ejected, 6 kilograms per second of small particles and 60 kilograms per second of larger grains, provides clues about the comet's surface activity. These measurements, combined with spectroscopic analyses of the Coma's composition, paint a picture of a dynamic, evolving object. The presence of cyanide gas and atomic nickel vapor, detected by the Very Large Telescope, further underscores the complexity of 3I Atlas's chemistry. Such compounds, common in solar system comets, hint at shared processes in the formation of planetary systems across the galaxy. The comet's trajectory, meanwhile, reveals its galactic heritage. By analyzing its velocity components in the galactic coordinate system, astronomers have determined that 3I Atlas likely originates from the Milky Way's thick disk, a population of older stars with lower metallicities than those in the thin disk. This origin suggests an age of at least 7 billion years, making 3I Atlas potentially older than the solar system itself. Tracing its path backward in time, we find that it entered the solar system from the direction of the galactic center, a region teeming with stars and interstellar matter. The fact that it has traveled for billions of years without being captured by a star speaks to the chaotic nature of galactic dynamics, where gravitational interactions between stars can eject objects from their natal systems. These revelations are not merely academic, they challenge our understanding of the universe's architecture. The existence of interstellar comets, like 3I Atlas, implies that planetary systems are not isolated entities, but part of a grander exchange network. Comets, asteroids, and other small bodies may serve as cosmic couriers, ferrying materials, and perhaps even the seeds of life between star systems. In this context, 3I Atlas is not just a visitor, it is a relic of the galaxy's turbulent history, a testament to the interconnectedness of all things. As we continue to observe its journey, we are not only deciphering the story of a single comet, but also probing the fundamental processes that shape the cosmos. The trajectory of 3I Atlas is a marvel of precision and timing. Its closest approach to the Sun, known as perihelion, will occur on 29 October 2025, at a distance of 1.36 AU, placing it between the orbits of Earth and Mars. This point marks the climax of its journey, where the Sun's gravitational pull accelerates the comet to its maximum speed of 68 kilometers per second. Yet, despite this velocity, 3I Atlas will remain a safe distance from Earth, never coming closer than 1.8 AU. Its path is meticulously mapped by a global network of observatories, from the Hubble Space Telescope to the ground-based Very Large Telescope, each contributing to a growing dataset that refines our understanding of its behavior. The comet's approach to the inner solar system has already yielded surprises. Observations by the Transiting Exoplanet Survey Satellite, TESS, revealed that 3I Atlas was active as early as 7 May 2025, when it was 6.4 AU from the Sun. At that distance, the sublimation of carbon dioxide and carbon monoxide, volatile ices with lower freezing points than water, drives its activity. This finding challenges conventional models of cometary behavior, which often associate high activity with proximity to the Sun. Instead, 3I Atlas's early outgassing suggests a nucleus rich in these volatiles, a composition that may reflect the conditions of its birthplace. As the comet draws nearer, its interactions with the solar system's planets offer a rare opportunity for indirect observation. On 3 October 2025, it will pass within 0.19 AU of Mars, a distance close enough for orbiters like NASA's Perseverance rover and ESA's ExoMars Trace Gas Orbiter to capture detailed data. These instruments may detect changes in the comet's coma, or tail, as it experiences the Martian environment, providing insights into the effects of planetary proximity on interstellar objects. Similarly, 3I Atlas will pass 0.65 AU from Venus in November 2025 and 0.36 AU from Jupiter in March 2026. While these encounters will not alter its trajectory significantly, they underscore the dynamic interplay between celestial bodies in the solar system. The challenge of observing 3I Atlas from Earth is compounded by its faintness. With an apparent magnitude of no brighter than 11.5, it remains invisible to the naked eye, and even to amateur telescopes. Professional observatories, however, have tracked its evolution with remarkable precision. From the Gran Telescopio Canarias to the Zwicky Transient Facility, Telescopes have captured the expansion of its coma from 13,040 kilometers in diameter in June 2025 to 18,760 kilometers by July. These measurements, combined with spectroscopic analyses, reveal a complex interplay of dust and gas. The comet's reddish hue, attributed to large organic molecules in its coma, mirrors the colors of solar system comets and D-type asteroids, suggesting a shared heritage of irradiation and chemical processing. Yet, for all the technological prowess deployed to study 3I Atlas, its true nature remains elusive. The comet's nucleus, shrouded in a veil of dust and gas, defies direct measurement. Early estimates of its size ranged from 10 to 20 kilometers, but subsequent Hubble observations narrowed this to a more plausible range of 0.32 to 5.6 kilometers. The discrepancy arises from the difficulty of disentangling the nucleus's intrinsic brightness from the coma's reflected light. This challenge is exacerbated by the comet's high activity, which continuously replenishes the coma with fresh material. Even as we refine our techniques, 3I Atlas reminds us of the limits of human perception in the face of cosmic phenomena. The debate over 3I Atlas's origins has also sparked a lively discussion among astronomers. While its trajectory and velocity components suggest a thick disk origin, the possibility of a younger, thin disk progenitor cannot be entirely ruled out. This ambiguity reflects the broader uncertainties in modeling galactic dynamics, where the motions of stars and interstellar objects are influenced by countless factors, from gravitational perturbations to dark matter. Theoretical models propose that 3I Atlas may have originated from a low metallicity star system, where the abundance of heavy elements is lower than in the solar system. Such an origin would align with its high carbon dioxide content, as CO2 forms efficiently in colder, less chemically enriched environments. Perhaps the most contentious issue surrounding 3I Atlas is the speculation about its artificial origins. In July 2025, astrophysicist Avi Loeb and colleagues proposed that the comet's anomalous trajectory and chemical profile might indicate an extraterrestrial spacecraft. This hypothesis, while provocative, has been met with skepticism by the broader scientific community. Most astronomers argue that the evidence for cometary activity, detected carbon dioxide, water vapor, cyanide, and nickel vapor, is overwhelming. Furthermore, the comet's hyperbolic excess velocity and trajectory align with natural ejection mechanisms, such as gravitational interactions with giant planets or passing stars. While the idea of an interstellar probe is enticing, the consensus remains that 3I Atlas is a natural object. This debate, however, underscores a deeper truth. The universe is full of mysteries waiting to be unraveled. Whether 3I Atlas is a comet or something else entirely, its journey through the solar system serves as a reminder of our ignorance and our capacity for discovery. Each observation, each data point, brings us closer to understanding not only this comet, but the processes that shape the cosmos. As we await its perihelion passage and the subsequent observations by the James Webb Space Telescope, we are left with a profound sense of wonder. In the quiet hum of 3I Atlas's approach, we hear the echoes of a universe teeming with possibilities. As 3I Atlas continues its journey through the solar system, it invites us to consider a question that has haunted humanity for centuries. Are we alone in the universe? The discovery of interstellar objects like 3I Atlas challenges our assumptions about the rarity of such phenomena. If the galaxy is indeed teeming with planets and planetary systems, why do we encounter so few interstellar visitors? Is the sheer scale of the cosmos a barrier to frequent exchanges? Or is there a deeper reason for this scarcity? This conundrum, known as the Fermi paradox, questions the apparent contradiction between the high probability of extraterrestrial life and the lack of observable evidence for it. While 3I Atlas is a natural object, its existence raises intriguing parallels. Just as we search for signs of intelligent life, we also seek to understand the origins and trajectories of interstellar comets. Both endeavors reflect our desire to connect the dots between the known and the unknown, to find patterns in the chaos of the cosmos. The rarity of interstellar objects like 3I Atlas may stem from the low frequency of planetary system interactions. Gravitational slingshots that eject comets into interstellar space are relatively uncommon, and the vast distances between stars make such ejections even rarer. Yet the fact that we have discovered 3 interstellar objects in just a few years suggests that our observational capabilities are improving. Future surveys, such as those conducted by the Vera C. Rubin Observatory, may uncover more of these cosmic nomads, expanding our understanding of their distribution and origins. At the same time, the debate over 3I Atlas's potential artificiality, though largely dismissed, highlights the enduring allure of the unknown. The idea that an advanced civilization might use interstellar objects as probes or vessels captures the imagination, even as the evidence leans heavily toward a natural explanation. This tension between scientific rigor and speculative curiosity is a hallmark of human inquiry. It reminds us that the pursuit of knowledge is not solely about answers, but also about asking the right questions. As we turn our gaze back to the heavens, 3I Atlas serves as a poignant symbol of our place in the universe. It is a reminder that the cosmos is both vast and intimate, a tapestry woven from threads of stardust and shared history. In tracing the journey of this comet, we are not only learning about its origin, but also reflecting on our own. What does it mean to be part of a universe where such visitors come and go, bearing gifts of insight and mystery? How do we reconcile our smallness with our capacity to dream, to explore, to seek? In the final moments of 3I Atlas's passage, as it departs the solar system and resumes its lonely voyage through interstellar space, we are left with a sense of humility and wonder. This comet, born in the crucible of another star system, has crossed the boundaries of the familiar to whisper its story to us. In listening, we are reminded that the universe is not a void, but a living, breathing entity, filled with the echoes of creation and the promise of discovery. As we prepare for the next chapter of our cosmic journey, let us carry forward the lessons of 3I Atlas, the importance of curiosity, the value of observation, and the enduring quest to understand our place in the infinite. In the vast expanse of the cosmos, where stars are born and die in silent titanic bursts, and planets drift in the hush of interstellar voids, 3I Atlas emerges as a fleeting yet profound reminder of the universe's interconnectedness. Discovered in the depths of Chilean skies on 1 July 2025, this interstellar comet is not merely a wanderer from another star system, it is a messenger, carrying secrets of ancient stellar nurseries and the chaotic dance of matter across galaxies. Its arrival in our solar system is an event as rare as it is wondrous, a collision of cosmic scales that bridges the familiar and the alien. As 3I Atlas hurtles through the inner solar system at 58 kilometers per second, faster than any interstellar object before it, it defies the gravitational pull of the sun, its hyperbolic trajectory a testament to its extraterrestrial origins. Yet, in its brief sojourn here, it offers more than a glimpse of the unknown. It invites us to reflect on our own transient existence. What does it mean to witness an object that predates our solar system, one that may have formed in the shadow of a long-dead star? How do we reconcile the vastness of the universe with the intimate realization that we share its building blocks with a traveler from another corner of the Milky Way? This comet is more than a scientific anomaly. It is a thread woven into the tapestry of the cosmos, binding together the fates of stars, planets, and perhaps even life itself. As we trace its path through telescopic lenses and spectral analyses, we are not merely observers. We are participants in a cosmic dialogue, one that stretches across billions of years and light years. 3I Atlas challenges us to see beyond the confines of our planetary home, to recognize that we are part of a grander narrative, one written in the languages of physics, chemistry, and time. To understand 3I Atlas is to unravel the threads of its origin, a journey that began not in the cradle of our solar system, but in the farthest reaches of the Milky Way. Its hyperbolic trajectory, defined by an orbital eccentricity of 6.141, places it among the fastest interstellar visitors ever recorded. Its velocity a relic of the gravitational forces that expelled it from its native system. The comet's path traces back to the direction of the galactic center, a region dense with stars and interstellar material. where its birthplace may lie in the thick disk, a population of ancient stars whose compositions whisper of the early universe. With an estimated age of 7.6 to 14 billion years, 3I Atlas predates the solar system by billions of years. Its nucleus, a fossil of an era when the Milky Way was young and turbulent. The composition of 3I Atlas reveals a story of extremes. Its coma, a swirling cloud of gas and dust, is rich in carbon dioxide, a compound rarely found in such abundance in solar system comets. This imbalance hints at a formation history unlike our own, perhaps in the frigid outer reaches of its parent star's protoplanetary disk, where CO2 frost lines allowed the molecule to condense into ice. The presence of water ice, water vapor, and carbon monoxide suggests a dynamic interplay between temperature and pressure, while traces of cyanide and atomic nickel add layers of complexity to its chemical profile. These elements, forged in the crucibles of ancient stars and scattered by supernovae, mirror the very atoms that constitute our own bodies and worlds. Yet 3I Atlas is not a static artifact. Its activity, driven by the sun's radiant energy, transforms it as it approaches perihelion. The sublimation of volatile ices creates a coma that evolves with time, its dust particles ejected in streams that trace the comet's path. The elongation of its coma toward the sun, a phenomenon observed in telescopic images, reveals the asymmetry of its nucleus, where sunlight preferentially heats certain regions. This dance of light and shadow, of ice and gas, is a microcosm of the universal processes that shape all celestial bodies. The comet's journey is also a lesson in the impermanence of cosmic structures. Though it will escape the solar system, its passage leaves an indelible mark on our understanding of the universe. Through instruments like the James Webb Space Telescope and the Hubble, we dissect its secrets with unprecedented clarity, peering into its CO₂-rich coma and mapping the contours of its nucleus. These observations are not mere data points. They are fragments of a puzzle that connects us to the origins of the cosmos. The arrival of 3I Atlas compels us to rethink the boundaries of our cosmic neighborhood. For millennia, humanity has gazed at the stars as distant, immutable lights. But 3I Atlas reminds us that the universe is a dynamic web, where objects travel, collide, and exchange material across vast distances. Every atom in our bodies was forged in stars, and 3I Atlas carries the same cosmic heritage. Its carbon dioxide, water, and organic compounds are echoes of stellar furnaces and molecular clouds. In studying this comet, we are not only deciphering the history of another star system, we are tracing the lineage of our own existence. This exchange of material is not limited to individual comets. The Milky Way itself is a river of interaction, where the gravitational tides of stars and dark matter stir the interstellar medium. Interstellar objects like 3I Atlas are the visible ripples in this cosmic current, their trajectories shaped by the unseen forces of the galaxy. The fact that 3I Atlas originates from the southern celestial hemisphere, a region previously underrepresented in interstellar object discoveries, underscores the need for broader observational efforts. It challenges assumptions about the distribution of such objects and highlights the limitations of our current vantage point. Moreover, 3I Atlas's journey raises profound questions about the universality of planetary systems. If comets can be flung into interstellar space by the gravitational antics of their host planets, what does this imply about the frequency of such events in other systems? Are interstellar objects as common as we suspect, or are they rare anomalies? The answer lies in continued observation and the development of technologies capable of detecting fainter, more distant travelers. Projects like the Vera C. Rubin Observatory, with its wide-field surveys, promise to uncover more of these cosmic nomads, expanding our understanding of the galaxy's interconnectedness. Beyond the scientific implications, 3I Atlas invites a philosophical reckoning. Its passage through the solar system is a reminder of the impermanence of all things. Just as this comet will vanish from our skies, so too will the Earth and the Sun fade into the cosmic night. Yet in this impermanence lies a paradoxical eternity. The atoms of 3I Atlas will persist, cycling through new stars, new planets, and perhaps even new life. The universe is not a static tapestry, but a living, breathing entity, its threads weaving and rewoven in an endless cycle of creation and transformation. As 3I Atlas departs the solar system, leaving behind a trail of questions and revelations, it serves as a catalyst for humanity's next steps in cosmic exploration. The challenges of reaching such a fast-moving interstellar object are immense, requiring propulsion systems and mission designs far beyond our current capabilities. Yet the very existence of 3I Atlas proves that interstellar travel is not a fantasy. It is a frontier waiting to be explored. Concepts like solar sails, nuclear propulsion, and even speculative ideas like warp drives take on new urgency as we contemplate the possibility of intercepting future interstellar visitors. For now, the focus remains on observation. Spacecraft like the James Webb Space Telescope and the upcoming Nancy Grace Roman Space Telescope will continue to scrutinize 3I Atlas as it recedes into the void, capturing data that may refine our understanding of its composition and behavior. Meanwhile, ground-based observatories, from the Canary Islands to Chile, will track its fading glow, a silent tribute to the collaborative spirit of global astronomy. These efforts are not just scientific endeavors, they are acts of cultural preservation, ensuring that the story of 3I Atlas is documented for generations to come. The Comet's journey also underscores the importance of international cooperation in space science. The discovery and study of 3I Atlas involved contributions from observatories across the globe, from the Atlas Survey in Chile to the Zwicky Transient Facility in California. This collective effort mirrors the interconnectedness of the universe itself, where no single nation or institution holds the keys to cosmic understanding. As we prepare for future missions, perhaps to intercept another interstellar object or to send probes to the outer reaches of the solar system, we must build on this foundation of collaboration, fostering partnerships that transcend borders and ideologies. Ultimately, 3I Atlas is more than a scientific curiosity. It is a beacon of inspiration. Its fleeting presence in our skies is a reminder that the universe is vast, mysterious, and alive with possibility. It calls upon us to look upward, not with fear or complacency, but with wonder and determination. For in the quiet glow of a comet's coma, we find a spark of curiosity that binds us to the cosmos, and a challenge to carry that spark forward into the unknown.